Welcome to Orbit Observer. It's lovely to have you here tonight. Wherever you are right now, tucked under a heavy blanket, lying on a couch with one lamp still glowing in the corner, maybe on a late train with your forehead resting against the cold window, I'm glad you found your way here. Settle in. There's nothing you need to do for the next little while. Nothing to solve, nothing to remember. Just let your eyes go soft, let your shoulders come down from wherever they've crept up to, and let me do the talking. And before we drift off into the dark together, I'm curious. Where in the world are you watching from tonight? What time is it in your corner of the night? I always wonder about that. Somewhere out there, someone is listening to this with the morning still hours away, and someone else is listening as the sky has only just gone purple. Whoever you are, wherever you are, it's good to have you with me up here. If you enjoy these slow journeys and you'd like more nights like this one, a gentle like and a subscribe really do help this sleepy little channel keep drifting along. Small creators like me rely on it more than you'd think. And to those of you who've already subscribed and keep coming back night after night, truly thank you. You're the reason the lamp stays on. Now, let me tell you something strange before we begin properly. Something that sounds almost made up, but isn't. There is a place not so very far from here, as these things go, where the air would melt the lead inside a pencil, where the temperature sits at around 465 degrees Celsius, that's roughly 870 degrees Fahrenheit, hot enough that solid metal would slump and run like candle wax. And while that heat was cooking you, the air itself would be pressing down on every inch of your body with the weight of standing nearly 900 meters underwater. Almost 3,000 feet down into a black ocean where no light reaches and the pressure could fold a submarine. That place is the planet Venus. And here's the part that always stops me, the little thread I want to pull on with you tonight. You might assume, most people do, that the deadliest, hottest world in our whole solar system would be the one sitting closest to the sun. It only makes sense, doesn't it? The nearer the fire, the worse the burn. And yet Venus is not the closest planet to the sun, not by a long way. There's a whole world that sits between Venus and our star, baking in the front row, much nearer to all that warmth. And that closer world isn't the hottest. It can't even hold a candle to Venus. So already, on the very first step of our journey tonight, the universe has quietly told us that we have it backwards. That's what I want to do with you over this slow, drifting hour. I want us to take a tour. A tour of every planet in our solar system, one by one, and ask a very simple, very strange question at each stop. What would actually happen if you appeared there right now, with no suit, no helmet, no ship? Just you, a soft, warm human body standing on each world in turn? What exactly would kill you? And, this is the interesting part, how fast and by what means? Because here's the thing I've come to find so quietly fascinating. We tend to imagine that dying on another planet is one single thing repeated 8 times over. Just, it's hot, or it's cold, or there's no air. But it isn't one thing at all. It's 8 completely different problems. 8 unrelated ways for the world around you to come apart your body. On one planet, your blood would boil before you ever felt the cold. On another, there would be nothing solid to stand on at all. You'd simply fall and keep falling, crushed by the air itself with no ground ever to land upon. On another, you'd be flash frozen while supersonic winds tore past you faster than the speed of sound. We're going to rank them, you and I. Not by how far they sit from the sun, which is the lazy way and the way most of these journeys are told. We're going to rank them by something more honest and a little more sobering, by how quickly and by what mechanism the human body actually fails on each one. And at almost every stop, the truth is going to surprise you, because the thing that gets you first is hardly ever the thing you'd guess. But, and I mean this, there is no need to follow every detail, no need to keep score, no need to remember a single number. If you drift off somewhere around the third or fourth world tonight, that's perfectly fine. That's rather the point. The planets will still be here when you wake, hanging in the dark exactly where we left them. I'll just keep talking softly, and you can let the words wash over you like a tide going out. Let yourself sink. No rush. We have all night, and we're going to take it slowly. So, let's begin, shall we? Let's start with that world I mentioned, the one that sits closest of all to the sun, basking in the front row, the one you'd swear must be the worst of them. Let's start with Mercury. Picture it for a moment. The smallest of the 8 planets, a little scorched ball of grey rock, pockmarked all over with craters like the surface of our own moon. It races around the sun closer than any other world, so close that from its surface the sun would loom in the sky far larger and far fiercer than we ever see it from our gentle blue home. You'd think, wouldn't you, that this is the oven, the hottest, harshest place to die in the whole family of planets. Front row to the fire, and in a way half of that is true. The day side of Mercury reaches around 430 degrees Celsius. That's 800 degrees Fahrenheit, genuinely scorching, more than hot enough to end you. So why then isn't Mercury the hottest planet? Why does Venus, sitting much farther back from the sun, beat it so easily? The answer is something Mercury simply doesn't have. A blanket. Let me explain that gently, because it's the secret to the whole thing. When we say a planet has an atmosphere, we mean it's wrapped in a layer of gas, air, more or less, held against its surface by gravity. And that layer does something we almost never think about down here. It holds on to warmth. It traps heat like a thick duvet pulled up to your chin on a cold night, keeping the warmth from escaping out into the dark. Earth has that blanket. Venus, as we'll see, has an enormously thick one. Far too thick, in fact, which is exactly why it cooks. But Mercury has almost nothing at all. What it has instead is something scientists call an exosphere. And it's such a thin, ghostly thing that calling it an atmosphere would be far too generous. Imagine a few stray atoms drifting about above the surface, a faint scattering of oxygen, sodium, hydrogen, helium, and a little potassium. So sparse, so spread out that they barely bump into one another at all. There's no real air there in any sense you or I would recognize. Nothing to breathe. Nothing to press against your skin. And crucially, nothing to hold the heat in. So here's the strange consequence. The day side of Mercury bakes to that fierce 430 degrees, but the night side, the half turned away from the sun, sitting in shadow, plunges to around minus 180 degrees Celsius. That's about minus 290 Fahrenheit, colder than almost anything you can imagine. The heat simply pours away into space the moment the sunlight leaves because there's no blanket to hold it. Think for just a moment about how vast that gap is, from over 400 degrees of scorching heat to nearly 200 degrees below freezing. That's a swing of more than 600 degrees Celsius between one side of the planet and the other. It is, in fact, the largest temperature swing of any planet in the entire solar system. One little world holding both the searing oven and the deep, deep freeze side by side, separated only by the line between day and night. And it gets stranger still because of how slowly Mercury turns. A single day on Mercury, by which I mean the time it takes for the sun to rise, cross the whole sky, set and rise again, lasts about 176 Earth days. Let that settle for a moment. Nearly half a year, just to go from one sunrise to the next. So when the dayside bakes, it doesn't bake for a few hours the way ours does. It bakes for months. The sun crawls across that black sky so slowly that the ground beneath it has time to soak in every bit of that brutal heat, day after day after day, with no relief. Now, let's put you there, gently. Just imagine you've appeared on the surface of Mercury, standing on that grey, cratered ground, the enormous sun hanging overhead. What happens to you? This is where the story takes its first surprising turn, the first of many tonight, because your mind probably leaps straight to the heat. 430 degrees, you'd burn, you'd cook. That must be the killer, surely. But it isn't. Not first. The thing that ends you on Mercury isn't the temperature at all, it's the nothing, the absence of any air to press on you. You see, here on Earth, we live our whole lives at the bottom of an ocean of air. We don't feel it, but it's pressing on us constantly from every direction. About 1 bar of pressure, we call it, 1 atmosphere. Our bodies are built for it, tuned to it, balanced perfectly against it. Every breath you take, the oxygen crosses from your lungs into your blood only because the air is pushing it there with enough pressure to do the job. Take that pressure away, and the whole delicate machinery simply stops working. And on Mercury, there is no pressure at all, none. Standing on its surface, with that ghost-thin exosphere offering nothing, is exactly the same as standing exposed in the deep vacuum of open space, the same as being flung out of an airlock with no suit. So what happens to a human body in a vacuum? It's not what the films would have you believe. You wouldn't explode. You wouldn't burst apart in some dramatic spray. Our bodies are mostly water and tissue, incompressible, sturdier than you'd think, held together by skin that's a good deal tougher than a balloon. So no, you wouldn't pop. The reality is quieter and somehow gentler and stranger. The first thing that would happen is that you'd lose consciousness, and it would happen fast, within about 15 seconds. There's a phrase for this that pilots and astronauts use, the time of useful consciousness. It's the window you have after the air is gone, before your brain runs out of oxygen and the lights go out. And in a true vacuum, that window is only around 15 seconds, a slow count to 15. That's all. After that, you'd simply slip away into unconsciousness, painlessly, without ever quite understanding what was happening. Why so fast? Because the oxygen doesn't just stop arriving, it actively leaves, with no pressure pushing oxygen into your blood. The oxygen already in your blood reverses course and seeps back out into the vacuum. Your body is emptied of the very thing keeping you awake, and your brain, the hungriest organ you own, is the first to feel its loss. And here's the detail that I find oddly tender, oddly human in all of this. Before you even lost consciousness in those first few seconds, something small and strange would happen. The saliva on your tongue would begin to boil, not from heat, from the lack of pressure. Let me unfold that for you because it's the key to so much of what's coming tonight. We tend to think water boils when it gets hot. At 100 degrees, the kettle sings, steam rises. But that's only true at the pressure we live in down here. Boiling isn't really about heat at all, not deep down. It's about the balance between heat and pressure. Lower the pressure, and water will boil at a lower and lower temperature. Climb a high mountain where the air is thinner and your kettle boils before it reaches 100. Keep lowering the pressure further and further, and you reach a remarkable point. Scientists have a name for it. They call it the Armstrong limit. And it's one of the quietly profound facts about being a fragile, watery creature in this universe. So let me say it plainly. The Armstrong limit is the pressure. Very, very low. Only about 6% of the pressure we feel here on Earth, at which water boils at the temperature of the human body. At 37 degrees Celsius, at your temperature, the warmth of your own living flesh. Do you see what that means? Above that limit, out where the pressure drops below it, as it does on Mercury, where there's essentially no pressure at all, the water in your body doesn't need any heat from outside to boil. Your own gentle body warmth is more than enough. The moisture on your tongue, the wetness of your eyes, the fluid lining your lungs, all of it begins very softly to turn to vapor, to bubble. There's a word for this happening inside living tissue: ebulism, the forming of vapor bubbles in your bodily fluids when the pressure falls away. Your blood wouldn't boil quite so easily because it's sealed inside your veins where there's still some pressure from your own circulation. But the exposed wetness, the tongue, the eyes, the lungs, that would begin to fizz gently into the vacuum. It sounds horrifying when I lay it out like that. But truthfully, you'd be unconscious within 15 seconds and you'd feel almost none of it. It's the kind of death that happens faster than understanding. A quick, quiet fading out there on that grey and cratered ground. And then, only then, after the vacuum had already claimed you, would the temperature have its turn. And which temperature gets you depends entirely on something almost absurdly simple: where you happen to be standing, whether you're in the sunlight or in the shade. Imagine you appeared on the day side beneath that enormous slow-crawling sun, the ground at 430 degrees. After the vacuum took your consciousness, the heat would slowly cook what was left, the way that fierce, unblanketed sunlight cooks everything it touches there. But step over to the night side, or even, in a way, imagine half of you in shadow, and instead of cooking, you'd be freezing. Minus 180 degrees, the heat leaching out of you into the endless cold dark. The same body, the same death, and yet entirely different aftermaths decided by nothing more than whether the sun could see you. There's something almost poetic in that, isn't there? That on Mercury you could, in the strangest sense, be cooking and freezing within the very same moment. The lit side of you roasting while the shadowed side froze. Because there's no air to blend the two, no blanket to soften the edge between light and dark. The atmosphere we take so utterly for granted, the one pressing softly on your skin right now as you lie there breathing, is the thing that keeps our own world's days and nights from becoming that violent. It mixes the warmth around. It carries heat from the sunlit places to the shaded ones, from day into night, smoothing it all into something a body can live through. Mercury has none of that. So it lives at both extremes at once, and so briefly would you. One more small kindness Mercury offers, though it's no help at all in the end. Its gravity is gentle, only about 38% of Earth's, so you'd feel light there, less than half your usual weight, the way an astronaut bounds across the moon. If you could somehow survive everything else, you could leap absurdly high, drift down slowly, feel almost weightless. But of course you can't survive everything else. The lightness would last about as long as that count to 15. So let's hold Mercury in our minds for a moment gently, before we move on. The closest planet to the Sun, the one you'd swear must be the hottest, the cruelest, the worst. And yet, here's our first surprise, the one that sets the tone for everything still to come tonight. It isn't the hottest at all. It can't hold its heat. It bakes on one side and freezes on the other, swings 600 degrees between them, and in the end, it's not the heat or the cold that takes you first. It's the silence, the empty, pressureless nothing, the vacuum that boils your own saliva with your own warmth and quietly switches off the lights in 15 soft seconds. The closest world to the fire, and it's almost an afterthought on our grim little ranking. Because the true oven, the genuinely hottest, most reliably lethal world in the entire solar system, is the one we glimpsed at the very start of tonight's journey. the one that melts the lead in a pencil while crushing you under an ocean's worth of weight. The one sitting farther from the sun than Mercury, and yet so very much worse. So let's leave this little scorched and frozen rock behind and drift on slowly toward that second world. Let's go and stand on Venus, Biddy, and finally answer the question of why the closest planet to the sun was never the hottest one at all, and what exactly would happen to you in a place that cooks and crushes and suffocates and burns you all at once in almost the same breath. But first, just rest for a moment here in the quiet. Let your breathing slow. Let the warmth of your own blanket remind you of how good and rare it is to be a soft, breathing body on the one world in all of this, where the air presses just gently enough and the warmth holds just kindly enough that you can lie here safely and listen and drift and be perfectly, wonderfully fine. Now, let's go on. Venus. It sits there in the dark, the second world out from the sun, and from a distance, it's the loveliest thing in our sky. The brightest point of light most nights, brighter than any star, soft and silver and serene. Sailors steered by it. We called it the morning star and the evening star before we understood it was a single planet wearing two names. Of all the worlds, it's the one that looks the most like a promise. A sister to Earth. Nearly the same size, nearly the same mass, formed from the same swirl of dust at nearly the same distance from the same fire. And it is, beyond any question, the worst place a soft human body could ever come to rest. Let's start with the thing you'd feel first, because on Venus, there's no gentle wait, no slow countdown like on the airless rocks. The moment you arrive, you are already inside an atmosphere, a real one, thick and heavy and crushing. And that changes everything about how you die. The temperature on the surface of Venus is about 465 degrees Celsius. Some measurements put it a little higher, around 475. Let that number settle for a moment because it's hard to hold in the mind. It is hot enough to melt lead. If you stood there with a pencil, the soft grey core inside it would slump and run like candle wax. Tin, lead, zinc. All of them would turn to silvery puddles on the ground. This is not a temperature that exists anywhere on the day side of any other planet in the solar system. Not on Mercury, baking for months under a sun 3 times larger in its sky. Not anywhere. Venus is the hottest planet there is, full stop, and it is hotter than the world that sits closer to the flame. Here's the part that feels almost unfair, the small injustice at the heart of it. Mercury is closer, Mercury gets more sunlight per square meter, far more, and yet Mercury, as we just saw, can't keep any of that warmth. It has no blanket, no air to hold the heat, so the moment the sun sets, the warmth simply pours away into space and the ground plunges down toward minus 180. Venus does the opposite. Venus holds everything. Nothing leaves. And the reason is the very thing that's about to crush you and choke you, all wrapped into one. The air on Venus is about 96.5% carbon dioxide. Almost the whole sky, the entire ocean of gas above the surface, is the same gas you breathe out when you exhale, the gas that traps warmth. On Earth, we have a thin, gentle scarf of it, just enough to keep us from freezing solid at night, just enough to make our world livable. Venus is smothered in it, a planet wrapped head to toe in a heat-trapping blanket so thick that sunlight slips in, warms the ground, and then can't get back out. The warmth builds and has nowhere to go century after century until the whole world settles into a single, even furnace-hot temperature that barely changes from the equator to the poles, from the blazing dayside to the long night. There is no cool place on Venus, no shade that saves you, no relief anywhere on the entire globe. This runaway warming has a name. Scientists call it the runaway greenhouse effect, and Venus is the most complete, most catastrophic example of it in the solar system. A world that long ago tipped over an edge and could never climb back. Some scientists believe Venus may once have had oceans, liquid water on its surface, billions of years ago. If it did, the warming boiled them all away, every drop, and the water vapor only thickened the trap, and the trap only deepened the heat around and around until nothing was left but this scorched and shrouded furnace. A cautionary tale written across an entire planet, hanging there in our evening sky. So that's the heat. Now feel the weight. Because Venus doesn't only cook you, it presses on you. The atmosphere is so thick, so dense, so heavy that the pressure at the surface is about 92 times the pressure here on Earth. 92 times. It's a number that doesn't mean much on its own, so let me give you something your body can feel. Imagine swimming down into the ocean, down past the warm shallows, past where the light starts to fade, down where the water turns dark and cold, and the weight of it begins to squeeze your chest and press against your ears. You'd have to descend about 900 meters, nearly a kilometer straight down beneath the waves, before the water pressed on you as hard as the simple air does on the surface of Venus. 3,000 feet of ocean bearing down, and that's just standing there in what Venus calls open air. Now here's a thing that surprises people, and it's worth being honest about because the truth is stranger than the cartoon. That pressure, all on its own, would not pop you like a balloon or crumple you like a deep-sea submarine. Our bodies are mostly water, mostly liquid, and liquid doesn't compress, just pushes back. So the pressure alone is not the implosion you might picture. But it doesn't need to be, because the pressure isn't working alone. Nothing on Venus works alone. The pressure and the heat and the airlessness arrive all together, in the same instant, in almost the same breath. So let's actually do it. Let's stand you on Venus just for a moment and trace what happens, slowly, in order, even though in reality it would all be over before you could finish a single thought. You appear on the surface. There is no sun visible. The clouds are far too thick for that, a permanent overcast of yellowish gloom. The light is dim and strange, like a heavy, hazy afternoon that never brightens and never ends. And almost at once the heat is inside you, not on you, in you. 465 degrees doesn't warm you from the outside the way a fire does. It floods you. The water in your skin, in your eyes, in your blood, all of it racing toward that temperature, and water cannot stay water at 465 degrees. It flashes. The moisture in your lungs, on your tongue, in your tissues, turning to steam in a heartbeat. Your fluids, in seconds, reaching a temperature no living cell can survive. This isn't a slow roasting, it's a near instant collapse of everything soft, everything that made you alive, all at once. And while that's happening, the weight is on you, that 92 bars pressing from every side, the dense hot air shoving in everywhere, and there's no oxygen, not a trace you could use, so even if the heat somehow spared you, there's nothing to breathe, only that smothering blanket of carbon dioxide. And as if all of that weren't already more than enough, the clouds themselves, those soft yellow clouds that make Venus glow so beautifully in our sky, are made of sulfuric acid, droplets of it drifting through the upper air. So even the gentle haze around you is corrosive, cooked, crushed, suffocated, chemically burned. 4 separate, complete, unsurvivable deaths, and Venus delivers all 4 at the same moment. You wouldn't experience them one after another the way I've had to tell them to you. You'd simply be, and then in the time it takes to register that you've arrived, you would not be. The most thorough, most absolute, most overlapping death of any world in the solar system, in a place that, from far away, looks like the prettiest light in the heavens. And here is the small, strange detail that I find lingers in the mind the longest, the one that turns it from a fact into something almost haunting. The gravity on Venus is about 90% of Earth's, nearly the same. Of all the planets, Venus pulls on you the most like home. So in those final, impossible instants, cooked and crushed and burning, your body would weigh almost exactly what it weighs right now, lying there under your blanket. You would feel almost normal, almost like standing on Earth, the one lethal world where the simple pull beneath your feet would feel like an ordinary afternoon, while everything else about the place tore you apart. A planet that feels, in that single sense, like home, and is in every other sense the farthest thing from it. Now you might be wondering, and it's a fair thing to wonder, how we could possibly know all of this, how anyone could measure the temperature, the pressure, the chemistry of a place that destroys whatever we send there. And the answer is one of the quietly heroic stories of the space age, and it belongs to a series of machines with a single plain name: Venera. The Venera program was a long campaign by the Soviet Union across the 1960s and 70s and into the 80s to do something that sounds almost impossible: to build a machine that could land on the surface of Venus and survive long enough to send something home. And world after world, probe after probe, Venus simply killed them. The early ones were crushed on the way down, flattened by that ocean of pressure before they ever reached the ground. Some were cooked, some went silent in minutes, their instruments cooking inside their own shells. Engineers learned and built tougher, heavier, thicker craft, spheres built like deep-sea diving bells, chilled before descent, armored against the weight, and sent them down again into the furnace, knowing the planet would win in the end every time. And it always did. The very best any of them managed, the absolute record for surviving on the surface of Venus, was a lander called Venera 13. It touched down in 1982 and it held on, transmitting, working, sending its measurements back through that crushing sky for 127 minutes, just over 2 hours, and then Venus destroyed it, the way it had destroyed all the others, the way it would destroy anything. 2 hours and 7 minutes. And that's the longest anything we've ever built has lasted on the ground there. But in those 2 hours, Venera 13 did something no machine had done before. It sent back the first color photographs ever taken from the surface of another planet. A flat, rocky, orange-tinged landscape under that dim and heavy sky, lit by a sun no one standing there could ever see. The first true glimpse of the ground of Venus, captured by a dying machine in the last hours of its short, brave life. So when I tell you it's 465 degrees, when I tell you it's 92 times Earth's pressure, these aren't guesses, they're the last words of a handful of small spacecraft that drifted down through the acid clouds and stood for a few impossible minutes in the worst place we have ever found, and told us what it was like before the silence took them too. Rest with that for a moment. The brightest light in your evening sky, the one you might have looked up at 1,000 times without ever knowing. A furnace wrapped in acid, heavier than the sea, hotter than molten lead. Beautiful from here. Unspeakable up close. And you, safe, soft, breathing, exactly where you should be. And now we pause there for just a moment in the strange warmth of that image, or the world of such extraordinary hostility, so close, glowing so gently in your sky. Venus. The answer to the question we opened with. Not Mercury. Never Mercury. Mercury is closer to the Sun, yes, and we'll come back to what that actually means for a person standing there. But hottest? Deadliest? Most certain to kill you most thoroughly and most quickly. That belongs to Venus. the runaway greenhouse effect, the carbon dioxide sky 92 times heavier than the air you're breathing now, the sulfuric acid clouds, the 465 degrees of heat that has nowhere to go, trapped forever under that thick blanket of atmosphere, the furnace that remembers nothing of what it might once have been. Venus wins. And it isn't close. But let's stay with it just a little longer, because there's one more thing about Venus that's quietly strange, and it has to do with how it would feel. Not the temperature, not the chemistry, how it would feel in your body in the seconds you lasted there. Venus has a surface gravity of about 90% of Earth's. 90%. You would step down if you could step down there, and your feet would meet the ground with almost the same weight they meet the ground here. Not quite the same. You'd feel very slightly lighter, the way you feel in an elevator just before it settles, a barely there, unweighting, but essentially, terrifyingly, you would feel normal. Your legs would carry you the same way they carry you down a hallway. Your arms would swing the same. The planet that is about to kill you faster and more completely than any other world in the solar system would, for that first fraction of a second, feel entirely familiar. Earth weight, Earth normal, the ground solid underfoot, the gravity almost indistinguishable from home, and then everything else. The heat first, because the heat is not something you walk into gradually. 465 degrees Celsius is not a summer afternoon turned up too high. It is far, far beyond anything the human body has a framework for. Your skin's pain receptors would be overwhelmed immediately. Your proteins would begin to denature, the same process that turns the white of an egg from translucent to solid, but happening in your tissues, in your blood. The moisture in your eyes would flash away. Your fluids, the ones that weren't already boiling from the pressure differential, would begin to cook. It would take, by any honest estimate, only seconds for the damage to reach a level that is simply incompatible with life. And the pressure is working alongside it, 92 times Earth's atmospheric pressure. Let's sit with that number for a moment, because it's the kind of number that doesn't quite fit in the brain until you find the right comparison. Earth's atmospheric pressure at sea level is 1 bar. We use that as our baseline, the normal, the thing we call comfortable. Venus's surface pressure is about 92 bar, and if you want to know what 92 bar feels like, you have to go underwater. Deep underwater. The pressure increases by roughly 1 bar every 10 meters of depth in the ocean. So 92 bars is the pressure you'd experience at approximately 900 meters below the surface of the sea. 900 meters. Not a scuba depth, not a recreational depth, not even a military submarine depth. We're talking about the kind of depth where the ocean becomes genuinely dark and still and cold, where the pressure will destroy almost anything not specifically designed to withstand it. Now here is where the physics gets interesting and where the popular picture gets it slightly wrong. People tend to imagine that this pressure would instantly and catastrophically crush you, the way a can gets crushed when you pump the air out. A sudden, spectacular implosion, but that's not quite right, because the human body is mostly liquid. Water doesn't compress your tissues, your blood, your organs. They're not hollow, they're not full of air, waiting to be squeezed out. They're dense, liquid, relatively incompressible. The pressure of Venus's atmosphere would not crumple you like an empty tin. It would squeeze you from all directions at once, yes. And that squeeze is enormous and unsurvivable, but the mechanism is different. It's more like the pressure bearing down on your joints, your ears, the gas-filled spaces in your lungs and sinuses. Those spaces would be catastrophically affected. The gas would compress or be forced out. The damage to your body's delicate gas-filled cavities would be extreme and immediate. But you wouldn't pop. You would cook, and you would be slowly and utterly crushed by the weight of all that atmosphere pressing in, while simultaneously suffocating in the 96.5% carbon dioxide air, while sulfuric acid from those high clouds drifted down and touched your skin. It is not one thing that kills you on Venus. It's the combination. The 465 degrees, the 92 bar pressure, the unbreathable air, and the chemical burns from the acid, all of them arriving at once. You have no way to survive any single one of them, let alone all four simultaneously. The kindness, if there is one, is that the heat is so overwhelming it dominates everything else. The cooking would render the experience, if we can call it that, very short. Venera 13 lasted 127 minutes, and it was made of metal and circuits, specifically engineered to survive. You, standing there with your 90% Earth normal weight under your feet, would last seconds. And then there would be silence, and the orange-tinged light, and the flat, rocky landscape photographed by that brave, dying machine, going on without you. Take a breath. You're still here. Let's come home for a moment. It's worth it, I think, to stop here, right in the middle of this tour, and just acknowledge what home is, what Earth actually is, as a place, as a set of physical conditions. Because we're about to visit worlds that kill you in elaborate and interesting ways, and it's easy to take for granted the rather extraordinary fact that this one doesn't. Earth. Surface pressure, 1 bar. Surface oxygen content, 21%. Average surface temperature, about 15 degrees Celsius. Liquid water covering most of the surface, drinkable in many places, stable as a liquid over a vast range of latitudes and seasons. Gravity that your body has spent its entire evolution calibrating itself to. Atmospheric composition that is precisely, narrowly, remarkably suited to keeping you alive without any effort on your part. You don't have to do anything special to be alive on Earth. You just have to be here. That's genuinely unusual. Of all the planets in this solar system, 8 of them, plus the collection of moons and dwarf planets and icy bodies drifting at the edges, Earth is the only one where a human body, unprotected, with no suit and no equipment, simply functions. Every other world on our list requires at minimum protection from pressure, or protection from temperature, or an oxygen supply, or all three at once, and often in combination with several more requirements besides. Earth isn't just the nice one. Earth is the only one. There is no second place. We mention this not to be grim, but because you're about to go to Mars, and Mars is the world that, more than any other in the solar system, looks like it might almost be survivable. From a photograph, from a distance, from the way people talk about it, Mars carries the suggestion of somewhere you could walk around and look at things and have experiences. It is, of all the places we're visiting, the one with the most surface area of plausible-looking terrain. Rocks, a horizon, a sky, albeit thin and orange-pink, dust. It looks like you could stand there. You cannot. Mars, the 4th planet. The one we dream about. The one with the rovers and the missions and the serious, ongoing plans to one day send human beings. The one that has inspired more science fiction, more engineering ambition, more genuine scientific excitement than perhaps any other body in the solar system except Earth itself. Mars is where we're going, in the minds of people who spend their careers thinking about where humanity might go next. And if you were simply teleported there right now, unprotected, standing on the Martian surface in whatever you're wearing, as you listen to this, you would be dead within minutes, probably within 2 minutes, possibly faster, not from the cold, not primarily, not first. Let's be precise about this, because the cold is the thing people remember about Mars, and the cold is real, but it is not the first killer, it is the second, or maybe the third. And understanding why requires understanding a concept called the Armstrong limit, which is one of the more interesting pieces of physics in this whole tour. The Armstrong limit, named for American Air Force physician Harry Armstrong, is the altitude, or equivalently the pressure level, at which water boils at human body temperature. 37 degrees Celsius. The temperature your blood runs at, the temperature of the moisture in your lungs, the temperature of the saliva in your mouth, and the tears in your eyes and the fluid in your joints. At sea level on Earth, water boils at 100 degrees Celsius, which is well above body temperature, so the water in your body remains liquid. But as you go higher, as the atmospheric pressure drops, the boiling point of water drops with it. At high altitude, you've probably heard that water boils at a slightly lower temperature. Pasta takes longer to cook on a mountain because the boiling point is reduced. Continue climbing and eventually you reach the Armstrong limit, at around 19 kilometers above sea level on Earth, where the pressure has dropped to about 0.06 atmospheres. At that pressure, water boils at 37 degrees Celsius. Your body temperature. The temperature your fluids already are. Above that altitude or below that pressure threshold, the water in your body would spontaneously begin to boil, not from heat, but from the absence of pressure to keep it as a liquid. This phenomenon is called ebullition. It is not a metaphor. Your saliva would literally bubble and boil on your tongue. The moisture in your lungs would begin to foam. The fluid in your eyes would start to vaporize at the surface. It would be painful and incapacitating and very fast. Now, the surface pressure of Mars is about 0.6% of Earth's, 6 millibars, not 6 bars, not 6%. 0.06 of 1% of Earth's atmospheric pressure. Earth's surface pressure, remember, is 1,000 millibars. Mars's is 6. The Armstrong limit is 61 millibars. Mars's surface is at 6. Mars is 10 times below the Armstrong limit. You are not merely above the altitude where fluids boil at body temperature. You are drastically, catastrophically below the minimum pressure at which a human body can function at all. The moment you appeared on the Martian surface, the pressure differential between the inside of your body and the outside would begin the process of ebullition. Your bodily fluids, the ones on or near the surface of your skin, in your eyes, in your lungs, in your mouth, would begin to vaporize. Your lungs would be trying to breathe an atmosphere that is 95% carbon dioxide, which means even if you could draw in a breath, there is no usable oxygen in it. You would begin losing consciousness from hypoxia, oxygen deprivation, within about 15 seconds. This is roughly the same time of useful consciousness as in a complete vacuum, because for practical purposes, Mars's 6 millibar atmosphere is, to your lungs, essentially a vacuum. So within 15 seconds, unconscious from hypoxia, ebullition beginning in your exposed tissues, your lungs unable to extract any useful oxygen from the near-vacuum atmosphere. And the cold, which is real and significant, is genuinely not the first thing. Mars's average surface temperature is around minus 63 degrees Celsius. That's minus 81 Fahrenheit. It is cold, genuinely cold, cold enough to be immediately and lethally dangerous in ordinary circumstances. But in the timeline of what kills you on Mars, the ebullition and hypoxia win the race. You'd lose consciousness in seconds. You'd be dead from the decompression and the oxygen deprivation within a couple of minutes. The cold would then continue to do what it does, but you would not be there to experience it. The popular image, frozen on Mars, standing stiff and ice rimed on the red surface, is half right. You would indeed freeze eventually, but you would suffocate and your fluids would boil first. It's worth noting, by the way, that Mars isn't uniformly that cold everywhere. At the equator, on a summer afternoon in the right location, the temperature can actually climb to about 20 degrees Celsius, plus 20, not entirely unlike a cool autumn day. This is one of the reasons Mars feels, in photographs and in imagination, like somewhere you could almost visit without incident. The daytime temperatures at the equator are not themselves the problem. The problem is the pressure. The temperature at the surface on that imaginary pleasant afternoon is still plus 20. and the pressure is still 6 millibars, and the atmosphere is still 95% carbon dioxide. A nice day in terms of temperature, a vacuum in terms of breathable air. At the poles in winter, the temperature drops to around minus 125 degrees Celsius. The atmosphere partially freezes, carbon dioxide frost on the polar caps, and there's nothing you could do about any of it because you'd have been gone long before you had time to feel the deep cold settle in. Gravity on Mars is about 38% of Earth's, the same as Mercury, as it happens, a coincidence of size and composition. You'd feel light there, almost bouncy. Each step would carry you a little further than expected, a little slower in the fall. Some part of you, if it were possible to be there safely, would love it. And then there's the dust. Mars has dust storms, genuinely enormous ones, global dust storms that can cover the entire planet, that block out the thin sun for weeks, that have been watched from telescopes and from orbit, and from the cameras of our various landed spacecraft. They look dramatic in images, and in fiction, they are even more dramatic. You've probably encountered stories where a Martian storm flings objects around, upends equipment, turns a gentle afternoon into a catastrophic wind event. Here's the thing about a Mars storm. The wind speeds are real because they can reach something like 150 miles per hour. In Earth terms, that's a serious hurricane-force wind. It would be enough to knock you down here, to rip the roof off a house, to carry substantial debris. But on Mars, those wind speeds occur in an atmosphere that is 60 millibars below the Armstrong limit. That is 167 times less dense than Earth's air. The force that a wind exerts depends not just on its speed, but on the density of the medium it's moving through. A 150 mile per hour wind on Mars carries the physical impact of a gentle breeze. Not a metaphorical breeze, a genuinely light, easy to ignore movement of air. The dust in such a storm would coat your suit, cover your solar panels, reduce visibility, but it would not pick you up and throw you. It would not fling your equipment. The dramatic storm sequences in some of our beloved Mars fiction are, from a physics standpoint, essentially impossible. The air is simply too thin to carry that kind of force. In a strange way, that's both reassuring and not. Reassuring because the storms wouldn't smash you, not reassuring because you would already be dead before the first gust reached you, having suffocated in the near vacuum that produces those harmless, impressive-looking hurricane winds in the first place. 38% gravity, 6 millibars of pressure, minus 63 degrees average plus 20 on a good afternoon, minus 125 at the poles, 95% carbon dioxide, below the Armstrong limit by a factor of 10. Mars, the dream. Mars, the plan. Mars, the place that looks, in photographs, almost plausible. Not plausible, not without a sealed suit, a pressurized habitat and an oxygen supply. Not for 1 second without those things. But the cold doesn't kill you first. That's the Mars fact to carry, the thing that gets the popular picture wrong. People hear Mars and they hear cold, and the cold is real, but it's the near vacuum that wins. The Armstrong limit. The water in your lungs trying to boil at body temperature in the absence of any meaningful atmospheric pressure. The embolism arrives before the frostbite. And Mars, unlike Venus, would kill you in a couple of minutes rather than seconds. Not better exactly. You'd still be very thoroughly dead, but slower. More time for the landscape to register, in some theoretical sense. More time for the thin pinkish-orange sky to make its impression, the sky that contains almost no usable air. More time for the dust-covered plains and the distant suggestion of a rust-red horizon to be the last thing your eyes transmitted to a consciousness that was already, by then, almost gone. Mars gets credit in the ranking of deaths for being slower. But that's all the credit it gets. Now let's talk about the two questions we've been holding open since almost the beginning. You've been patient. We've moved from Mercury, with its vacuum death and its cooking or freezing, to Venus, the reliable killer, the hot press of 92 atmospheres and 465 degrees. We've paused at Earth and let the ordinariness of it, the extraordinary narrow ordinariness, land for a moment. And we've been to Mars, where the cold is not the first thing, and the near vacuum boils your fluids before the freezing can take hold. 4 worlds, 4 different ways to die, but there are still 4 more planets, and 2 of them are the ones that people most often get wrong in their imaginations. The gas giants, Jupiter and Saturn, the enormous planets that fill up so much of the solar system's volume and carry so much of its mass. And the question people most often ask about them is some version of, how long before they crush you? It's a reasonable question. They are, after all, called gas giants. They're enormous, they're heavy. Jupiter's mass is more than twice that of all the other planets in the solar system combined. Saturn is the second largest. They feel, in imagination, like they should be crushers. Like the thing they do is compress. And they do compress. But before we get to the crushing, there's a more fundamental issue. A more surprising issue. You can't stand on Jupiter, not because it would crush you the moment your foot touched down, but because there is no down, there is no surface, there is no ground. You've heard this, perhaps, that Jupiter is a gas giant, that it has no solid surface. But the full strangeness of that fact takes a moment to really absorb. Because when we say Jupiter has no surface, we don't mean the surface is hidden somewhere under clouds, the way Venus's surface is hidden but genuinely there. We mean that there simply is no boundary, no line, no threshold where the gas ends and something solid begins. The atmosphere just gets thicker, the pressure increases, the temperature rises, the gas transitions at enormous depth into something more like a liquid, a very strange, very hot, very compressed liquid, and then, deep in the interior, at crushing pressures that dwarf even Venus's 92 bar, it transitions into something stranger still. But there is no surface in the ordinary sense of the word, no place to put your foot. So the question, how long before Jupiter crushes you, has a different answer than you'd expect. The answer begins with, you fall. You appear at the cloud tops. Let's say we teleport you there, to the visible upper atmosphere of Jupiter, the layer we can see from telescopes and from our passing spacecraft, the layer with those great swirling bands and storms. You're there, at the cloud tops with no ground beneath you. And immediately, because Jupiter's gravity at the cloud tops is about 2.5 times Earth's, you begin to sink. 2.5 times Earth's gravity means you weigh 2.5 times your normal weight. Every part of you is being pulled downward at 2.5 times the acceleration you're used to. Your legs, if they were somehow holding you up, would be bearing 2.5 times the load. Your heart would have to work harder to circulate blood against that pull. You'd feel heavy immediately and dramatically in a way that would make walking difficult and standing for long periods impossible, even if there were something to stand on. But there is nothing to stand on, so you fall. And as you fall, as you sink downward through the cloud layers of Jupiter, the pressure around you begins to rise. At the cloud tops, it's already low. Colder than anything we'd recognize as comfortable, about minus 145 degrees Celsius at the cloud tops. Cold enough to kill you efficiently, though in the context of what's coming, the cold at the top is almost the gentlest part of the experience. As you sink, the pressure increases, the temperature increases. The gas around you thickens. It presses in from all sides, the way water presses in as you dive deeper in the ocean, but far more quickly and far more extremely. Within a few hundred kilometers of descent, the pressure reaches thousands of bars, not 92, the way Venus manages to kill you on its surface. thousands. At those pressures, the hydrogen that makes up most of Jupiter's atmosphere behaves in ways that are simply unlike anything we encounter at human scales. It compresses into forms that are intermediate between gas and liquid. It resists, it pushes back, and it pushes back on you on every surface of your body in ways that would destroy any biological structure long before you reached the more exotic depths. Deep inside Jupiter, at pressures so extreme they're almost abstract, something genuinely strange happens to the hydrogen. It stops behaving like a gas or even a liquid and begins to behave like a metal. Metallic hydrogen. Hydrogen so compressed that its electrons move freely through it the way electrons move in a conductor. This is the material that generates Jupiter's enormous magnetic field, that swirling, powerful magnetosphere that stretches millions of kilometers into space. You would never reach this region. Long before you reached it, the pressure and the heat, which rises to thousands of degrees in the interior, would have rendered you into something with no recognizable human structure at all. There is somewhere a core to Jupiter, a region of compressed rock and ice and exotic materials at the very center. Its exact nature is still a subject of active research, but it is, by any estimate, at crushing pressures and temperatures that are thousands of degrees, and it is thousands of kilometers from where you began your fall. You would never make it there. You'd be dissolved and compressed into the atmosphere long before you were a fraction of the way down. This is the genuine physical answer to what would Jupiter do to you. It would never crush you against a surface because there is no surface. It would crush you with the weight of its own atmosphere, pressing in from all sides as you sank, deepening around you like an ocean with no floor, until there was nothing left of you that the planet recognized as distinct from itself. And before any of that, before you even reached the upper atmosphere, before the pressure began to build, there is another problem. A problem that operates at a distance before you even arrive. Jupiter has radiation belts. Enormously powerful ones generated by that metallic hydrogen interior and the vast magnetic field it creates. The radiation environment around Jupiter is genuinely lethal at a level that makes the environments of the other planets look mild. The probes we've sent to Jupiter, the Galileo spacecraft which orbited Jupiter from 1995 to 2003, and the Juno spacecraft which is still there now, still in orbit, still sending back data, are both heavily shielded against Jupiter's radiation. Galileo was deliberately crashed into Jupiter at the end of its mission, partly to prevent its defunct radiation-battered systems from contaminating any potentially life-bearing Jovian moons. Juno's orbit is specifically designed to minimize its time in the most intense parts of the radiation belts. For a human being, unshielded, in the vicinity of Jupiter, the radiation dose would reach fatal levels within hours, not from the atmosphere, not from the pressure, from the radiation environment of the space surrounding the planet before you'd even entered the atmosphere to begin your endless fall. So Jupiter kills you in two stages. First, the radiation belts would fatally dose you as you approached, if you were anywhere near the planet for any length of time. And then, if you somehow survived that and entered the atmosphere anyway, you would fall and fall and fall, pressed into nothingness by the thickening gas, never touching ground, compressed and heated, and ultimately incorporated into the planet itself. No dramatic surface impact, no satisfying crunch of landing, just the long, heavy, increasingly dense and hot fall into a planet that has no floor. Jupiter? The largest, heaviest, most radiation-drenched, most relentlessly gravitational world in the solar system. And the one that kills you, not by crushing you on impact, but by making the very concept of impact impossible. Let's keep moving, because Saturn is waiting, and Saturn has a surprise of its own. Saturn, as planets go, is something of a contradiction. It is the second largest world in the solar system. It has a diameter nearly 10 times Earth's. It is ringed by one of the most beautiful structures in the known universe, a vast, flat disk of ice and rock stretching hundreds of thousands of kilometers into space. And yet, for all of that immensity, if you could find an ocean large enough to hold it, Saturn would float. That's not a metaphor or an approximation. Saturn's average density is about 0.687 grams per cubic centimeter. Water is 1.0. Saturn is less dense, on average, than the water in a bathtub. You could fill a hypothetical ocean the size of the planet, and Saturn would bob on the surface like a colossal, ringed, entirely impossible rubber duck. It is the lightest world by density in the solar system, and it still kills you. The method is familiar by now. Saturn is a gas giant. There is no surface. If you materialized somewhere above Saturn's cloud tops, you would not land. You would fall exactly as you would on Jupiter, through deepening layers of gas, hydrogen and helium at first, thickening gradually, pressure mounting with every kilometer of descent. Saturn's cloud top temperature sits at around negative 178 degrees Celsius. Not the coldest place we'll visit, but cold enough that the first moments of your arrival are a breath of gas at temperatures that freeze flesh nearly instantly. And then the winds find you. Saturn's equatorial winds reach approximately 1,800 kilometers per hour, just over 100 miles per hour. These are not gusts, these are sustained, planet-girdling jet streams that have been howling without interruption for longer than human civilization has existed. They would not simply push you. At those speeds, in a dense enough gas, they would tear. And as you fell deeper, the density would increase and the pressure would build, and the temperature would rise, and the story would end in exactly the same way Jupiter's story ended. Pressed out of existence by a planet that has no floor and no ceiling, only a direction that goes down and down until there is no you left to go any further. The gravity at Saturn's cloud tops is about 1.07 times Earth's, barely more than what you feel standing in your kitchen. Given how enormous the planet is, that number feels wrong. You expect something crushing, something that announces its scale. But the low density compensates. Saturn is vast, but it is mostly empty of mass compared to its volume. So you would fall through it feeling almost your normal weight right up until the pressure made that irrelevant. There is, in Saturn's death, a particular kind of melancholy. Jupiter is overwhelming. The radiation, the scale, the gravity, the sheer aggression of the place. Saturn feels visually quieter. Those rings, that pale gold. In photographs, it looks like something from a dream. But it would kill you in exactly the same way, through the same mechanism, with the same absence of ground to stand on. The beauty is real, it just isn't friendly. Now, we move outward. And here is where the solar system gets strange in a different way. Because the next two worlds, Uranus and Neptune, are a different class entirely. Jupiter and Saturn are gas giants built primarily from hydrogen and helium. Uranus and Neptune are what planetary scientists call ice giants. That name is slightly misleading because the material inside them is not frozen solid. It is a hot, dense, pressurized fluid mixture of water, methane, and ammonia. Not quite ice, not quite water, something in between, squeezed under conditions that don't exist naturally anywhere on Earth, but the name has stuck, and so ice giants. Uranus arrives first, seventh planet from the Sun. And Uranus holds a record that surprises almost everyone who hears it. The coldest measured atmospheric temperature in the solar system does not belong to Neptune, the farthest planet. It does not belong to Pluto, the demoted dwarf planet drifting beyond Neptune's orbit in the freezing dark. It belongs to Uranus. Uranus's atmosphere has been measured at temperatures reaching negative 224 degrees Celsius, the coldest planetary atmosphere we have ever recorded. Why? That question is still not completely settled. Neptune is farther from the Sun, and yet its atmosphere is warmer. The leading explanation involves the strange tilt of Uranus. The planet rotates at an axial tilt of about 98 degrees, meaning it essentially rolls on its side around the Sun, likely the result of a catastrophic collision with a very large object billions of years ago. This tilt affects how Uranus radiates its internal heat. Neptune radiates more internal heat than it receives from the Sun. Uranus, anomalously, does not. And so Uranus runs cold, colder than the world farther out. If you arrived on Uranus above its cloud tops, which is the only place you could be, because Uranus too has no solid surface, only that same deepening fluid mantle below the atmosphere, you would enter air at negative 224 degrees Celsius. Flash frozen immediately. The word instantly gets used a lot in this tour, but Uranus earns it as purely as any world will visit. The cold here is not the cold of a winter night, or a mountain summit, or even Antarctica. It is the cold of a world that barely remembers heat. The methane in the atmosphere absorbs red light and reflects blue-green back into space, which is why Uranus looks like a pale turquoise marble in photographs. You would fall through that turquoise cold, suffocating, frozen, and descend into the hot, dense fluid beneath. Crushed eventually, as you always are on these worlds without flaws. Uranus is also tilted so severely that its seasons last decades. One pole faces the Sun for roughly 42 Earth years, then the other. The planet experiences extremes of light and darkness on timescales that are difficult to fully grasp. None of this would matter to you as a human being arriving there unprotected. You would not last long enough to notice a season change. But it is worth knowing, if only because it tells you how thoroughly unlike Earth these worlds are. Not just in temperature or pressure, in the fundamental rhythm of time itself. And then Neptune. Neptune is the last planet, the farthest from the Sun since Pluto was reclassified by the International Astronomical Union in 2006, demoted from planet to dwarf planet in a decision that has annoyed a certain category of person ever since, but which reflects real differences in how Pluto formed and where it sits. Neptune now holds the outer edge of the planetary solar system, approximately 4.5 billion kilometers from the Sun. It receives about 1/900th of the sunlight that falls on Earth. Its cloud top temperature is around negative 214 degrees Celsius, not quite as cold as Uranus for the reasons we just discussed. Neptune leaks internal heat, Uranus mostly doesn't. But Neptune has something else. Neptune has the fastest sustained winds of any planet in the solar system, around 2,100 kilometers per hour, roughly 1,300 miles per hour. That is faster than the speed of sound in Earth's atmosphere. These are supersonic winds, planet-wide, unceasing, driven by mechanisms that involve Neptune's internal heat engine interacting with its distance from the Sun in ways scientists are still working to fully understand. If you arrived at Neptune, you would be flash frozen. The negative 214 degrees takes that from you immediately, or very nearly so. And simultaneously you would be hit by winds moving faster than sound. The combination is not survivable in any sense that needs elaboration. You would freeze and be blasted apart in the same instant, and whatever remained of you would fall, as always, into the deepening atmosphere below, crushed, as with all the giants, into the planet's interior. Neptune is, in a certain sense, the most honest of the dramatic-sounding deaths this solar system offers. When people imagine being destroyed by a planet, they often picture something like Neptune. The cold, the violence, the sheer hostile remoteness of a world that barely knows the Sun exists. And Neptune delivers on that image more faithfully than most. The flash freezing is accurate, the supersonic wind is accurate, the fall into the deep is accurate. Neptune does not disappoint. But now we need to go back. because we have been moving outward, planet by planet, and we skipped something. We left a loop open early in this journey when we talked about Mercury, closest planet to the Sun, expected to be the hottest, famously not. And we said the answer was coming. Here it is. Venus, the second planet from the Sun. The one that glows brighter than anything in the night sky except the moon, so bright you can sometimes see it in daylight, so bright sailors have mistaken it for an approaching ship's light. Venus, which looks soft and luminous and almost welcoming from a distance, Venus is the most reliably lethal world in the solar system for a human being, not the most dramatic, Neptune's supersonic winds or Jupiter's endless fall might claim that, but the most effective, the most thorough, the most efficiently fatal. The surface temperature of Venus is approximately 465 to 475 degrees Celsius, around 870 to 900 degrees Fahrenheit. That is hot enough to melt lead. It is hotter than the surface temperature on Mercury's day side, even though Mercury is nearly twice as close to the Sun. It is hot enough that the rocks on the Venusian surface glow faintly in infrared. And the reason Mercury is cooler has everything to do with what Venus has and Mercury doesn't. Venus has an atmosphere. A thick, dense, almost unimaginably heavy atmosphere composed of approximately 96.5% carbon dioxide with clouds of sulfuric acid drifting through the upper layers. That atmosphere acts as a blanket, a runaway greenhouse effect that has been trapping solar heat for billions of years, building and building until the surface temperature stabilized at a point that makes the inside of a kitchen oven feel refreshing. Mercury, with no real atmosphere, cannot hold heat. The sunlight strikes the surface and bounces away into space. The side facing the Sun bakes to around 430 degrees Celsius. The side facing away drops to around negative 180 degrees. Mercury cycles between those extremes because there is nothing to trap the warmth. Venus traps everything. The atmospheric pressure at the surface of Venus is approximately 92 times Earth's atmospheric pressure. To find a comparable pressure on Earth, you would need to descend roughly 900 meters below the surface of the ocean, about 3,000 feet down, well into the darkness where the weight of the water above is enough to crush most things. Now here is where intuition leads people wrong. When they hear 92 times atmospheric pressure, they imagine being instantly crushed, like a submarine hull failing at depth, the sides collapsing inward in a catastrophic implosion. But that is not what happens to a human body. A submarine hull is hollow, full of air. The pressure differential between inside and outside is enormous, and the structure collapses because there is a void to collapse into. A human body is mostly liquid, mostly water, and liquids do not compress easily. You are, in a crude but useful sense, already full. So the 92 bar pressure on Venus does not implode you the way it implodes a hollow metal sphere. What it does is add to the catastrophe rather than being the catastrophe by itself, because on Venus you are not dealing with one cause of death, you are dealing with all of them simultaneously. You are being cooked at 465 degrees Celsius. At that temperature, your body's water begins to flash to steam. Your proteins denature in fractions of a second. The heat alone would kill you faster than you can process what is happening. You are breathing nothing, or trying to breathe nothing, because the 96.5% carbon dioxide atmosphere contains no usable oxygen. You are suffocating even as you are cooking. You are being pressed from every direction by a pressure equivalent to standing on the ocean floor nearly a kilometer down, which, even if it does not implode you outright, adds its weight to every other process, destroying your tissues. And the sulfuric acid clouds, while primarily an upper atmosphere phenomenon rather than a ground-level one in their densest form, contribute to a chemical environment hostile to biological material in ways that require no imagination to understand. The cooking and the pressure and the suffocation together are effectively instantaneous catastrophic tissue failure. There is no sequence to pass, no moment where the cold kills you before the pressure or the acid before the heat. It all arrives at once. And here is the detail that makes Venus uniquely unsettling among all of this. The gravity on Venus is approximately 90% of Earth's, the closest of any planet to what you feel on the surface of our own world. You would feel almost normal weight as all of this happened to you. No floating, no crushing heaviness, just the ordinary, familiar, everyday sensation of standing upright, while everything else was catastrophically, immediately wrong. We know exactly how lethal Venus is because we sent machines there and watched them die. The Soviet Venera program launched a series of landers toward Venus beginning in the 1960s. Early attempts were crushed or cooked before they could return meaningful data. The engineers kept redesigning, kept reinforcing, kept trying to build something that could survive long enough to tell them anything. Venera 13, which arrived at the Venusian surface on the 1st of March 1982, was their most successful. It touched down, survived the landing, and began transmitting data. It returned the first color images of the Venusian surface, a desolate, orange-lit, rock-strewn plain under a thick orange sky. It lasted exactly 127 minutes before the planet destroyed it. Not a design flaw, not a malfunction. 127 minutes was approximately how long the best engineering the Soviet space program could produce was able to hold out against a world that runs at 465 degrees Celsius under 92 times atmospheric pressure. The record still stands, so. Before we move on, let's place Venus where it belongs. If Mercury was the surprise and the closest planet, not the hottest, killing you like deep space, Venus is the resolution, the hottest planet, the most reliably lethal, the one that looks gentle from a distance and turns out to be the most thorough instrument of destruction in the solar system. It answers the loop we opened at the start. Which world is actually the worst? By the specific standard of how quickly and how completely a human body is destroyed and how little can be done about it, Venus stands apart. Now, between Venus and the outer giants, there is a world we need to treat honestly as a baseline and as a contrast. Earth. 1 bar of pressure. 21% oxygen. An average surface temperature of around 15 degrees Celsius. Liquid water. The thing you evolved for in every detail across 4 billion years. Earth is included in this tour not because it kills you, it is the only world in this survey that doesn't, but because without it as a reference, the numbers for every other world lose their meaning. 1 bar of pressure means something because you know what 1 bar feels like. 15 degrees Celsius means something because you know what 15 degrees feels like. Earth is the control. It is the single data point in this entire solar system that the human body was designed to inhabit. Every other world in this tour is a variation on what happens when one or more of those conditions is removed. Which brings us to Mars. Mars is the world most people have a mental image of. Red desert, thin air, cold nights, dust storms. And in that mental image there is a specific sequence of death. You step onto Mars without a suit, and the cold kills you. The temperature is negative 63 degrees Celsius on average, and at the poles in winter it reaches negative 125. That sequence, the cold first, the cold as the killer, is wrong. The cold is real, the cold is brutal, but the cold is not what kills you first on Mars, and understanding why requires the same piece of physics that explained what happens on Mercury, the Armstrong limit. The Armstrong limit sits at a pressure of roughly 0.0618 atmospheres, about 6.18% of Earth's sea level pressure. At and below this pressure, water boils at 37 degrees Celsius, human body temperature. The moisture in your eyes, the saliva in your mouth, the fluid lining your lungs, all of it begins to vaporize. This condition is called ebulism, and it is exactly as unpleasant as it sounds. Gas bubbles form in your bodily fluids. Your tissues swell. The process is not instantly lethal by itself, but it is immediately and catastrophically debilitating. The atmospheric pressure on Mars is approximately 0.6% of Earth's, or about 6 millibars. That is well below the Armstrong limit, far below it. So when you arrive on Mars without a suit, before the cold has time to penetrate your body, which takes seconds to minutes, the near vacuum is already at work. There is no usable oxygen partial pressure at 6 millibars even in the thin Martian air, which is 95% carbon dioxide in any case. You cannot breathe. Your time of useful consciousness in a vacuum environment is around 15 seconds. Within a couple of minutes, hypoxia and the effects of ebulism have done their work. You suffocate and your fluids begin to boil. Then you freeze. The cold is the second act, not the first. The frozen solid Mars body of science fiction is half right. You do eventually freeze, and you freeze hard, down to temperatures that make most of Earth's winters look mild. But by the time that happens, the story is already over. There is one more Mars myth worth dismantling here, because it comes up whenever someone raises the planet in the context of danger. The dust storms. Mars experiences dust storms large enough to cover the entire planet. In 2018, a global dust storm lasted for months and was one of the factors that ended the Opportunity rover's mission. In the film The Martian, an astronaut is flung and nearly killed by a Martian dust storm. It is vivid and dramatic and feels scientifically plausible. But at 6 millibars of pressure, the Martian air is so thin that even winds reaching 150 miles per hour would carry approximately the same force on your body as a gentle breeze on Earth. The air has almost no mass to it. Wind force depends on air density, and Martian air has almost none. A 150 mile per hour Mars wind would ruffle your hair if you had any left to ruffle, which, given the other things happening to your body, you wouldn't by that point. The dust storms are real. The danger they represent to equipment, covering solar panels, reducing visibility, abrading surfaces over years, is real. The drama they represent for an unprotected human body is not. The wind does not kill you on Mars. The near vacuum does, and it does it first. So Mars, the most Earth-adjacent world in this solar system, the one humans most frequently discuss visiting, the one with the rovers and the orbiters and the plans and the ambitions, Mars kills you quietly, not with drama, with absence. The absence of pressure, the absence of oxygen, the absence of a thick enough envelope of air to keep your body's water in the state it needs to be in. It is, in its way, the most instructive death on this tour. Because Mars looks survivable, it looks like a cold desert, and the thing that makes it unsurvivable is invisible. And then there are the worlds where the question itself changes shape. We have talked about surfaces so far, about standing on rock, on dust, on the cold crust of a world and asking what kills you first. Mercury's airless expanse, Venus's crushing furnace, Mars's invisible, treacherous near vacuum. In every case, there was at least somewhere to stand, something solid under what would have been your feet. Now we arrive at the gas giants and the question, what happens if you stand on each planet meets a problem it was not prepared for? There is nowhere to stand. This sounds like a technicality. It is not. It is the single most important fact about the 4 outer giants in this solar system, and it is also the thing that popular imagination most consistently gets wrong. The image that people carry out of the gas giants as enormous alien worlds that would crush you instantly the moment you landed presupposes a surface, a moment of arrival, a place where your feet touch down and the planet responds. There is no such moment, there is no surface, there is no arrival in that sense. And so when we ask what happens to a human body on Jupiter, we are not asking a landing question, we are asking a falling question. Let's go to Jupiter. Imagine you have been brought here by some impossible means, some perfect, frictionless transport that places you, without speed, without a spacecraft, simply inside Jupiter's outer atmosphere, at the cloud tops, the place where the planet's visible faces, those swirling orange and brown and cream bands you've seen in photographs since you were a child. The first thing you notice is your own weight. You weigh 2.5 times what you weigh on Earth. That's the surface gravity at Jupiter's cloud tops, about 2.5 times Earth's. If you weigh 70 kilograms on Earth, you feel like you weigh 175. Every limb, every organ, the whole structure of you presses down into itself. Your heart strains a little harder to push blood upward. Your joints feel the load. You sag slightly into yourself. But you don't land. Because there is nothing to land on. You are in atmosphere. You have been placed inside a planet-spanning ocean of gas, and gas offers no solid resistance to your weight, only fluid resistance, the kind that slows but does not stop a falling object. And so you fall. The cloud tops are cold, about minus 145 degrees Celsius, roughly minus 234 degrees Fahrenheit. It is frigid, dark between the churning clouds, lit only by the distant pale sun, which from Jupiter appears about 5 times smaller than it does from Earth. You are not breathing and there is no oxygen. The atmosphere is primarily hydrogen and helium. And so ebulism and hypoxia begin immediately, as they did on Mars, as they did on Mercury. You lose useful consciousness within roughly 15 seconds, but here, the cold is almost beside the point because you are sinking. A human body has a density close to water, roughly 1 gram per cubic centimeter. The gas surrounding you has a much lower density at the cloud tops. You sink through it the way a stone sinks through air, faster at first, then slowed as the atmosphere thickens below you. And it does thicken. Jupiter is not a uniform cloud of gas that goes all the way through. As you descend, the atmosphere becomes denser, hotter, more compressed. Each layer you pass through has higher pressure than the last. At first, the pressure rises gradually, then less gradually, then not gradually at all. At a depth of a few hundred kilometers and not far on a planet with a radius of nearly 70,000 kilometers, the pressure has reached into the thousands of bars. To give you a sense of that number, the deepest point in Earth's ocean, the Challenger Deep, sits under pressure of about 1/100 bars. You would reach that kind of pressure relatively early in your descent into Jupiter, and then keep going through pressures the ocean floor of Earth has never known. The temperature has been climbing too. The minus 145 degrees of the cloud tops is a memory. Below the cloud layers, the temperature rises steadily, hundreds of degrees, then more, as the weight of the atmosphere above compresses everything below it, and compression generates heat. Deep inside Jupiter, temperatures reach into the tens of thousands of degrees. You are not alive to experience any of this, of course. You lost consciousness near the top, but your remains, whatever the heat and pressure have left of them, continue to sink, and the deeper they go, the stranger the environment becomes. At a great depth, the hydrogen, ordinary hydrogen, the lightest element, the stuff of stars, the stuff that makes water along with oxygen, undergoes something extraordinary. It is compressed so intensely that it transitions into a state called metallic hydrogen. Metallic hydrogen is not a gas, and not a solid, and not quite a liquid as we understand those things. It is hydrogen in a state where the electrons have been forced free of their atoms, the way electrons move freely in a copper wire. It conducts electricity. It flows, and it fills an enormous portion of Jupiter's interior, generating the planet's massive magnetic field, which is the strongest of any planet in the solar system. It is one of the stranger environments that exists anywhere in the solar system. Hydrogen behaving like a metal, carrying current, rotating with the planet, generating magnetic fields that stretch millions of kilometers into space. Your remains, by this point, are part of the chemistry of that descent. There is no solid core to land on, not in any simple sense. The metallic hydrogen transitions to something at the very center, possibly a dense, hot region of heavier elements. But the boundary between atmosphere and core on Jupiter is nothing like the boundary between ocean and seafloor on Earth. There is no seafloor. There is only increasing density, increasing heat, increasing pressure, all the way down. There is no bottom to stand on, there never was. And there is one more thing, something that would end the journey before the journey even truly began, before you had descended very far at all, before the pressure and the heat had time to do their full work. Jupiter has radiation belts. All the giant planets have magnetic fields, and magnetic fields can trap charged particles, electrons and protons and ions streaming from the Sun into intense belts of radiation surrounding the planet. Earth has such belts too, the Van Allen belts. They are dangerous to spacecraft and astronauts in certain orbits, but manageable with appropriate precautions. Jupiter's radiation belts are not manageable in any ordinary sense. The intensity of radiation in the regions surrounding Jupiter, particularly around the inner moons, is extraordinary. A human being placed unprotected near Jupiter in the region of its radiation belts would receive a radiation dose that would be lethal within hours, not days, hours. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, was heavily shielded against this radiation and still accumulated radiation damage over its mission. The Juno spacecraft, which arrived at Jupiter in 2016 and continues to orbit and study it, carries a radiation-shielded electronics vault, a titanium box protecting its most sensitive instruments, because even a robotic spacecraft's electronics can be destroyed by Jupiter's radiation environment if they are not shielded. A human body has no titanium vault, no radiation shielding. The DNA in your cells, the enzymes running your metabolism, the electrical signals in your nervous system, all of these are vulnerable to ionizing radiation in ways that metal and glass and plastic simply are not. At the doses available near Jupiter, acute radiation syndrome would begin almost immediately. Nausea, vomiting, damage to the cells lining your intestines, damage to the bone marrow that produces your blood cells. The process accelerates. It is not a gentle death. So in honesty, the question of what kills you on Jupiter has multiple answers depending on exactly where near Jupiter you are. Far enough away in space to miss the worst of the radiation belts, you fall into the atmosphere and sink and are crushed and cooked. Close enough to the radiation belts first, you are irradiated before you fall. There is no version of a visit to Jupiter that ends well, and there is no surface. That is the deepest answer. The thing that upends the image, the crushing is real, but it is the crushing of a thing falling through thickening gas, not the crushing of a thing standing where the weight of the world presses down on it. The gas giant does not greet you. It absorbs you. Now let's move outward. A little. Saturn, the second gas giant, the sixth planet from the Sun, the one with the rings. And if Jupiter felt overwhelming, Saturn offers something that, by comparison, almost feels like a joke, though the punchline is still lethal. Saturn is the least dense planet in the solar system. Let that sit for a moment. Saturn, with its rings and its storms and its enormous system of moons, is made of material so light, mostly hydrogen and helium in those outer layers, that its average density is lower than the density of water. Saturn's mean density is approximately 0.69 grams per cubic centimeter. Water is 1 gram per cubic centimeter. If you had a bathtub large enough to hold a planet, and it would have to be a very large bathtub, roughly 120,000 kilometers across, and you filled it with water and placed Saturn in it, Saturn would float. This fact, delivered in a classroom or in a book, tends to produce a small, delighted sound. It seems impossible. It seems like the kind of thing that can't be true about something so enormous and so dramatic and so present in our imagination as Saturn. And yet there it is, sitting in the dossier, solid as anything, average density less than water. It would float. Of course, this does not make Saturn gentle. The density of water is not the density of something friendly, and the average density includes the deep interior, which is dense. The outer atmosphere is what brings the average down, and the outer atmosphere is what you would encounter first. The cloud tops of Saturn are cold, about minus 178 degrees Celsius, which is roughly minus 288 degrees Fahrenheit. If Mercury's day side cooked you at 430 degrees and Venus cooked you at 465, Saturn's cloud tops are on the opposite extreme, well below anything you'd encounter in an Earth winter, cold enough to freeze oxygen itself into a liquid if you could collect it there. But again, there is no surface. As with Jupiter, you fall. Here's an interesting detail though. Saturn's gravity at the cloud tops is about 1.07 times Earth's. You would weigh only 7% more than you do right now. That is a surprisingly gentle number for the second largest planet in the solar system. The reason is that low average density. Saturn is enormous, but it is so spread out, so diffuse in its outer layers, that the gravitational pull you feel at the cloud tops is almost exactly what you feel on Earth. If someone told you before your visit to Saturn that the gravity would feel almost like home, you might feel a flicker of false comfort. And it would be false, because you are still falling, still breathing nothing, still sinking into thickening gas that has no floor. And the wind. If Jupiter was quiet in its destruction, efficient in its crushing fall, Saturn offers something more dramatic. The winds at Saturn's equator reach speeds of about 1/800 kilometers per hour. That is roughly 100 miles per hour. To put that in comparison, the speed of sound in Earth's air at sea level is about 1,025 kilometers per hour. Saturn's equatorial winds are approaching that speed, shrieking across a planet-spanning band tens of thousands of kilometers wide, never stopping, driven by Saturn's internal heat and its rapid rotation. These are not gusts. These are sustained, permanent features of Saturn's atmosphere, rivers of wind that have been flowing at those speeds for as long as we have been watching, and almost certainly far longer. The longest-running storm on Earth, a hurricane, lasts weeks. The wind bands on Saturn may have run for millions of years. If you were placed at Saturn's cloud tops, the wind would catch you the moment you arrived, not like a Mars wind. Mars's winds are nothing, wispy things carrying no mass. Saturn's atmosphere, even at the cloud tops, has actual density. The wind here has force. It would tear, it would buffet. And then, as with Jupiter, you would begin to sink through the layers into increasing heat and pressure, the wind fading as the atmosphere thickened around you until the pressure and the temperature finished what the cold and the suffocation had started. Different path than Jupiter, same destination, no surface, no bottom, just the long, crushing fall. There is something almost philosophical about the gas giants taken together. They represent the universe's refusal to play by the rules we set for it. We ask, what is it like to stand on them? And they answer by not having anywhere to stand. The question is dissolved by the nature of the thing. They are so large, so fundamentally gaseous in their outer layers, so unlike the rocky worlds we evolved on, that the frame of the question, the frame that works on Mercury and Venus and Mars, simply does not apply. You cannot step onto Jupiter any more than you can step onto a cloud. The cloud is just enormous and deep enough to swallow you entire, with nothing left to find. Now we go to two worlds that are neither gas giants nor rocky planets. They occupy a strange middle ground, denser and stranger inside than the gas giants, colder than almost anything else in the solar system. Uranus and Neptune are the ice giants, and they have a few surprises of their own. Let's start with Uranus. Uranus is the seventh planet from the Sun, discovered in 1781 by William Herschel, the first planet to be discovered with a telescope rather than by naked eye observation over centuries. It is large, about 4 times the diameter of Earth, and it is, in terms of its atmosphere, in one very specific and measurable way, the coldest place we have ever pointed an instrument at in our solar system. Not the farthest from the Sun, just the coldest. This is the question that the dossier planted earlier, and now we are here to answer it. The farthest planet from the Sun is Neptune. You would expect Neptune to be the coldest. Distance from a heat source should mean less heat, and Neptune is colder than Uranus in most ways. We'll get there. But Uranus's cloud top temperature has been measured at approximately minus 224 degrees Celsius. That is roughly minus 371 degrees Fahrenheit. That is the coldest measured atmospheric temperature in the solar system. Neptune, farther out, colder by instinct, comes in at about minus 213 degrees at its cloud tops, 10 degrees warmer than Uranus, up high, where we measure these things. Why? Neptune generates its own internal heat. Like Jupiter and Saturn, Neptune radiates more energy outward than it receives from the Sun. It has an internal heat source, the leftover warmth from the planet's formation still slowly leaking out. That internal warmth heats the atmosphere from below, raising the measured temperature slightly at the cloud tops. Uranus, in a peculiarity that planetary scientists are still working to fully understand, seems to radiate very little internal heat. It is, in this way, cosmically understated, a planet that should be blazing in the infrared, but is instead, somehow, almost thermally inert. The result is that its cloud tops are the coldest in the solar system. The distinction belongs to the quieter, stranger of the two ice giants. Uranus is also tilted, and not just a little. Every planet rotates on an axis, and every axis is tilted at some angle relative to the plane in which it orbits the Sun. Earth's axis tilts about 23.5 degrees, giving us seasons. Mars tilts about 25 degrees, giving it seasons too. Saturn tilts about 27 degrees. Even Jupiter, which is enormous, tilts about 3 degrees. Uranus is tilted about 98 degrees. The conventional image of a planet spinning on its axis like a top on a table does not apply to Uranus. Uranus rolls. It orbits the Sun essentially on its side, its poles pointing roughly toward and away from the Sun over the course of its year, which lasts about 84 Earth years. One pole faces the Sun for approximately 42 years in a kind of permanent day, while the other is plunged into permanent night. Then the situation slowly reverses. The most likely explanation is a collision, an ancient, enormous impact early in the solar system's history, when the planets were still young and impacts were more common. Something the size of roughly 2 Earths, or perhaps slightly smaller depending on the model, struck the young Uranus at such an angle that it knocked the planet sideways. And there it has stayed, rolling around the Sun ever since. This is a fact that takes a moment to properly absorb. A world that has been rolling on its side for billions of years, its poles cycling through decades-long days and nights, simply because of one violent collision in the deep past. The solar system is not a tidy, planned thing. It is the outcome of chaos that has mostly settled down. Now, what is Uranus actually made of? This is where the name ice giant becomes interesting, because the ice is not ice in the way you might picture it. Uranus has a thick outer atmosphere of hydrogen and helium, familiar from Jupiter and Saturn, but beneath that lies the mantle that gives the ice giants their name, a dense, hot fluid of water, methane, and ammonia. On Earth, these substances are familiar. Water is a liquid or a solid. Methane is a gas we use for cooking. Ammonia we encounter in cleaning products. At the temperatures and pressures inside Uranus, they are none of those things. They exist in a hot, dense, high-pressure fluid state, sometimes called superionic, or simply described as a mixture of ices. Not frozen, but compressed and energized into something that behaves like neither solid, nor liquid, nor gas in any everyday sense. This is the mantle through which you would descend if you entered Uranus, not through gas that thickens into metallic hydrogen, as on Jupiter, but through an atmosphere of hydrogen and helium that eventually gives way to this crushing, hot, strange fluid ocean of water and methane and ammonia under unimaginable pressure. There is no surface here either. But the death on Uranus has a distinct quality, a character different from Jupiter's. On Jupiter, the cloud tops are cold, the deeper layers hot. The temperature reversal is dramatic. You start in the deep cold and warm as you fall, the heat rising to meet you from below, until you are surrounded by temperatures in the thousands of degrees. On Uranus, those cloud tops are the coldest air anywhere in the solar system, minus 224 degrees Celsius. If the journey to Jupiter began in cold and ended in searing heat, the journey into Uranus begins in something colder than almost any other place you could visit. The cold is the headline here. The cold is the opening fact. The atmosphere of Uranus has another quality worth pausing on. It contains methane, not in enormous quantities by mass, but enough. Methane makes up roughly 2 or 3% of the upper atmosphere. And methane does something interesting with light. It absorbs red light very efficiently, allowing blue and green wavelengths to bounce back. The result is that Uranus appears in photographs as a smooth, pale blue-green sphere, one of the most featureless-looking planets in the solar system, a kind of cosmic blank, almost peaceful in its uniformity. The color is telling you something about the chemistry. The blue-green is methane's fingerprint written in light. So if you were placed in Uranus's upper atmosphere, the coldest in the solar system, remember, a place where you are already losing consciousness from lack of oxygen, and the pressure is already below anything that can sustain liquid water in your body, the first sensation would be the cold. Minus 224 degrees hits everything at once. Exposed tissue freezes almost instantaneously. The moisture in your airways and on your skin would freeze in a fraction of a second. Your body, falling through an atmosphere that offers little oxygen and even less warmth, would be simultaneously suffocating and freezing, and then you sink. Deeper into the atmosphere, the temperature and pressure rise as they do on the gas giants. The hydrogen and helium thicken around you, and then eventually comes the transition, that boundary where the clean gas atmosphere gives way to the hot, dense, fluid mantle of compressed water and methane and ammonia. This is a boundary unlike anything on the rocky worlds. There is no sharp line. The atmosphere just gradually gets denser, hotter, more pressurized, the hydrogen and helium mixing with increasing amounts of these heavier compounds until you are truly inside the mantle itself, not floating in gas anymore, but immersed in something thicker, weirder, hotter than any liquid you've encountered. The pressures in the mantle are in the millions of bars, temperatures in the thousands of degrees. The same region where exotic physics might be happening. Models of Uranus suggest that deep inside, the pressures could be high enough to compress carbon atoms into diamond, which would rain downward through the mantle as solid crystal before being crushed and dissolved at even greater pressures below. Diamond rain. It is one of the stranger theoretical predictions in planetary science, and it applies to both Uranus and Neptune. The conditions in the ice giant mantles may genuinely allow for the creation of diamond crystals in the high-pressure, high-temperature fluid. They form, they fall, they are eventually dissolved or crushed at still greater depths. A rain of diamonds in the belly of a planet, in a place where the pressure and temperature make ordinary matter behave in extraordinary ways. You would not see it, but it might be there, falling alongside the slowly dissolving chemistry that was once a human body, somewhere inside the coldest atmosphered planet in the solar system. The cold is Uranus's particular calling card. The silence, too, and is visually the most featureless of the giants, smooth and nearly bland, compared to Jupiter's storms or Saturn's rings or Neptune's wild winds. But beneath that smooth surface is everything you'd expect of a world that has been rolling on its side for billions of years, battered by ancient impacts, hiding its strange, icy interior under a deceptively serene face. If Uranus is the quiet giant, the one that hides its strangeness under a smooth blue-green mask, Neptune is the opposite. Neptune is the one that wears its violence openly. And Neptune is where we are going next. But first, a moment of stillness. You are still in bed or on your couch or somewhere comfortable where the temperature is maintained within a range that permits human life. A range, we are discovering, that is impossibly narrow compared to the options the solar system offers. On Uranus's cloud tops, it is minus 224 degrees. In Venus's lower atmosphere, it is 465 degrees above zero. The difference between those two numbers is nearly 700 degrees, and Earth, where you are right now, sits at an average of about 15 degrees Celsius, in a band so absurdly specific that it seems almost contrived, as if someone measured carefully and placed us here. No rush. We'll get to Neptune in a moment. Let the strangeness of Uranus settle. A world rolling on its side, colored blue-green by methane with the coldest air in the solar system, a mantle of compressed hot water, and ammonia and methane under crushing pressure, possibly raining diamond deep inside. Discovered by telescope in 1781 and studied ever since, and still holding questions that planetary scientists work on today. It doesn't look dramatic, it looks almost peaceful, that smooth blue-green sphere. And yet, now, Neptune. Neptune is the 8th and farthest planet from the Sun. Farthest since August 24, 2006, when the International Astronomical Union, meeting in Prague, voted on a definition of planet and reclassified Pluto as a dwarf planet, leaving Neptune alone at the edge of the solar system's planetary family. Before that date, depending on where Pluto was in its eccentric orbit, Neptune was sometimes the farthest and sometimes not. Now it is simply the farthest. Always. It sits about 4.5 billion kilometers from the Sun. That is roughly 30 times farther from the Sun than Earth is. The sunlight that reaches Neptune has been traveling for about 4 hours by the time it arrives, and it delivers about 1/900th of the energy that the same light delivers to Earth. The Sun from Neptune's cloud tops would appear as a very bright star. Brilliant, still the brightest object in the sky, but unmistakably a point of light rather than a disk, tiny and cold and distant in a way that no photograph taken from Earth or Earth orbit can quite convey. Neptune is one of the two ice giants. Like Uranus, no solid surface. Like Uranus, a hydrogen-helium outer atmosphere over a mantle of hot, dense, compressed water and methane and ammonia. Like Uranus, no place to land, only a place to fall into. But unlike Uranus, Neptune is violent in a way you can see from space. Neptune has the fastest sustained winds in the solar system. The winds at Neptune reach approximately 2,100 kilometers per hour. That is roughly 300 miles per hour. The speed of sound in Earth's air at sea level is about 1,025 kilometers per hour. Neptune's winds are supersonic. They break the sound barrier, the barrier that fighter jets and supersonic aircraft work hard to reach, that requires enormous engineering and expense and is considered a significant achievement of human technology. And they do it permanently, continuously, over a planet-spanning storm system driven by forces that we still do not entirely understand. Neptune radiates nearly 3 times as much energy as it receives from the Sun. Unlike Uranus, Neptune clearly has that internal heat source, that slow outpouring of the energy left over from the planet's formation billions of years ago. Models suggest that this internal heat, combined with the cold of space at Neptune's distance from the Sun, creates enormous temperature gradients in the atmosphere, enormous differences in temperature between one layer and the next, and that these gradients drive the ferocious winds. The mechanism is similar to what drives winds on Earth: temperature differences creating pressure differences which create movement. But at Neptune, the scale and speed are of a different order. The surface gravity at Neptune's cloud tops is about 1.14 times Earth's, slightly heavier than Earth. Not dramatically so. If you arrived at Neptune, you would feel a little heavier, not much. Your body would not know from gravity alone that you were somewhere extraordinary. What your body would know immediately, however, is everything else. The temperature at Neptune's cloud tops is approximately -214 degrees Celsius, that is -353 degrees Fahrenheit. This is colder than liquid oxygen. It is colder than liquid nitrogen, which boils at around -196 degrees Celsius. It is approaching what physicists call absolute zero from the opposite direction, the thermometer going as low as it can go. It is about 59 degrees above absolute zero, the theoretical floor of all temperature, the point where all thermal motion ceases. And those winds are already hitting you at 200 kilometers per hour. On Mars, we noted that even a 150 mile per hour wind felt like a gentle breeze because the air was so thin. Neptune's atmosphere at the cloud tops is far denser than Mars's surface atmosphere, not as dense as Earth's sea level air, but far, far more than Mars. The wind here has mass behind it. The wind here carries force, a 2,100 kilometer per hour wind in air, dense enough to push you. That is not a breeze. That is an impact. That is something that doesn't just push you, it tears at you. It is moving faster than the speed of sound. It carries the kind of kinetic energy that leaves marks. You would be frozen and blasted simultaneously. The flash frozen on Neptune image from the title of this video is, among all the dramatic images in this entire tour, probably the most physically accurate. That exact combination, the extreme cold, the supersonic wind, is not an exaggeration. Neptune genuinely would flash freeze exposed tissue while simultaneously hitting you with winds that break the sound barrier. It would do both things at once, simultaneously, in the first fraction of a second of your arrival. And then, as with Jupiter and Saturn and Uranus, the falling would begin. Sinking through the atmosphere, the temperature and pressure changing as you descend, eventually reaching that mantle of compressed hot fluid, eventually being crushed into the chemistry of a world that receives 1/900th of Earth's sunlight. Neptune has one famous feature, the Great Dark Spot, first observed by Voyager 2 when it flew past in August 1989, the only spacecraft ever to visit the planet. The Great Dark Spot was a storm system the size of Earth, a swirling dark oval in the southern hemisphere. When the Hubble Space Telescope turned its attention to Neptune several years later, the Great Dark Spot was gone, vanished. A new dark spot had appeared in the northern hemisphere. Neptune's storms are not the permanent fixtures that Jupiter's storms seem to be. They come and go on timescales of years, though the winds that create them never stop. Voyager 2 is the only visitor. Launched in 1977, it flew past Neptune in 1989 and has been traveling outward ever since, now well beyond the planets into the cold, dark region between the solar system and interstellar space. Everything we knew about Neptune from close range came from those few days in August 1989, when Voyager 2 passed through and sent its images back across 4.5 billion kilometers. The images showed a planet more vivid and dynamic than anyone expected. Deep blue, shot through with white clouds of methane ice crystals, storms and winds and complexity. A world at the edge of the solar system's family that did not look like an afterthought. Neptune earned its place, and it would earn its place in this ranking too. Of the four gas and ice giants, Neptune is the one where the death is most immediate and most spectacular at the moment of arrival. Jupiter's radiation is perhaps the most medically alarming, but the cold and the wind of Neptune are the most visceral, the most fully felt in the body's immediate surface experience before the deeper crushing began. Flash frozen at -214 degrees, hit by supersonic wind, then falling. There is no surface. There is never a surface out here among the giants. These four worlds, Jupiter, Saturn, Uranus, Neptune, collectively contain more than 99% of the mass of all the planets in the solar system. They are the solar system's dominant members, and not one of them has a place to stand. The question asked by this video's title: what happens if you stand on every planet one by one, hits a wall at Jupiter, and does not recover until we leave the 8 planets and go to the bonus bodies? The gas giants and ice giants cannot be stood on. They absorb you. They render the question moot. That is itself a fact worth carrying with you. The solar system we casually gesture at when we say 8 planets contains within that group 4 worlds so fundamentally different from the rocky inner planets that a human body cannot even meaningfully arrive on them. Mercury, Venus, Mars, these are places where the body fails, but they are places the body can go. Jupiter, Saturn, Uranus, Neptune. These are places where the concept of going there dissolves before the body has a chance to fail in any structured way. You fall. You are absorbed. You leave no mark. So we have now been through 6 of the 8 planets: Mercury, vacuum death, extreme temperature swing, ebulism, hypoxia, the cooking or freezing depending on where you stand. Venus, the reliable killer, fastest and most total, cooking and pressure and acid and suffocation all at once. Earth, the baseline, the control, the miracle. Mars, the invisible death, the near vacuum that kills before the cold can, the suffocation and boiling of the Armstrong limit. Jupiter, the fall with no bottom, the radiation belts, the crushing by thickening gas. Saturn, the same endless fall, the 1/800 km/h wind, the float in a bathtub density that disguises an inescapable trap. Uranus, the coldest atmosphere anywhere, the methane blue-green face hiding a strange rolling world, the mantle of compressed hot fluid, the diamond rain that might be falling somewhere in its depths right now. And now Neptune. Flash-frozen, supersonic, sinking. The farthest planet, the most windswept, the one that Voyager 2 visited once in 1989 and that no spacecraft has returned to since. 7 planets down, 1 more to go, and then the bonus bodies, which hold one of the most satisfying surprises of the whole tour. Neptune sits at the outer edge of everything we call the solar system's neighborhood. Not the very outer edge that belongs to the scattered disk, the Oort cloud, the long, cold suburbs of comets and ice, but the outer edge of the familiar, the named, the 8 worlds we grew up learning in order. It is, since the International Astronomical Union's 2006 reclassification of Pluto, the farthest planet from the Sun. And the numbers that describe its distance are the kind that stop making sense if you think about them too long. About 4.5 billion kilometers, 4.5 billion. To put that in terms your body can feel rather than your brain simply registering: light moving at 300,000 kilometers per second, takes about 8 minutes to reach Earth from the Sun. It takes roughly 4 hours to reach Neptune. When you look at Neptune through a telescope, which requires a good one, it is invisible to the naked eye. You are seeing light that left the Sun 4 hours earlier than the light that's warming your bedroom window right now. You are, in a gentle sense, looking back in time, 4 hours into the past. And because Neptune is so far from the Sun, it receives barely any of its warmth. About 1/900th of the sunlight that Earth receives. If you held up a piece of paper in Neptune's sunlight, it would cast a shadow, all but barely. The Sun from Neptune's surface would look like a very bright star. Not a disk, not the great warm coin of light we know, just a star, bright and piercing, but small, cold and remote. Neptune's cloud top temperature is about -214 degrees Celsius, -353 degrees Fahrenheit. That is, in the context of our tour, a familiar order of magnitude by now. Uranus, as we've just been through, manages -224 degrees, which is colder, and that remains the coldest atmosphere officially measured in the solar system. Neptune is slightly warmer in its upper atmosphere, oddly enough, because Neptune generates its own internal heat and pushes it outward. But -214 degrees is not a number that offers much comfort. It is more than twice as cold as the coldest temperature ever recorded at Earth's surface. It is cold enough that most gases we know as gases would have long since frozen solid and drifted down as snow. But the cold is not really what Neptune's reputation is built on. Neptune's defining characteristic, the thing that separates it from Uranus, even though they are siblings in almost every other sense, both ice giants, both blue-green from methane, both swathed in layers of compressed hot fluid beneath a hydrogen-helium atmosphere, is the wind. Neptune has the fastest sustained winds in the solar system, 2,100 kilometers per hour, roughly 1,300 miles per hour. That is supersonic, not metaphorically, not approximately. The winds on Neptune move faster than the speed of sound does in Earth's atmosphere. On Earth, we talk about supersonic aircraft as extraordinary achievements of engineering. On Neptune, the wind speed that would shatter the sound barrier here is simply the ordinary background weather. It is not a storm. It is not a seasonal event. It is Tuesday. The most famous storm on Neptune is known as the Great Dark Spot, first observed when Voyager 2 flew past in 1989. A storm system comparable in size to Earth itself, swirling at the edge of this already violent wind regime. By the time the Hubble Space Telescope turned to look at Neptune in 1994, the Great Dark Spot had vanished. Gone. Replaced later by new spots, new storms, coming and going in Neptune's restless atmosphere with a casualness that suggests the planet treats Earth-sized hurricanes as minor weather events. And Voyager 2, that single brief visit in 1989, is all we have. One spacecraft, one flyby, and then nothing. No orbiter has ever circled Neptune. No probe has ever descended into its atmosphere. We have gathered what we know from that single encounter, from telescopes, from inference. Neptune is, in some ways, the least known of the 8 planets, the farthest, the most difficult to reach. Now, you appear at Neptune's cloud tops in the same impossible thought experiment that has carried us this far through the solar system. No suit, no ship. Just you and the planet. You are moving at the speed Neptune orbits the Sun. You are hovering somehow at the level where the clouds begin. And then, as with Jupiter and Saturn and Uranus before it, there is nothing beneath your feet. No surface. No ground. Ice giant like Uranus beneath the hydrogen-helium atmosphere is a mantle of hot, dense, pressurized fluid made of water, methane, and ammonia, compressed to a state that doesn't behave quite like any of those things do at ordinary temperatures. Below that, a small rocky core at pressures and temperatures that are difficult to even describe in terms a human body has reference points for. But none of it is solid in any way you could stand on, so again, there is no standing, there is only falling. But the falling on Neptune is different from the falling on Jupiter or Saturn. The cold here meets you first. Negative 214 degrees Celsius wraps around you in an instant, cold beyond anything we have language for from ordinary experience. The deepest winter you have ever felt, the sharpest cold you have ever stepped into, these are utterly inadequate comparisons. What Neptune's temperature would do to an unprotected human body is closer to what liquid nitrogen does to a rose in a chemistry demonstration. The familiar structure of the thing suddenly becomes fragile, crystalline, and then it shatters. The cold does not negotiate, it does not creep in slowly the way a winter's night does. At negative 214 degrees, the thermal gradient between Neptune's atmosphere and your body's core temperature of 37 degrees Celsius is so enormous that the heat moves out of your body at a rate your physiology has no mechanism to resist. You are not chilling. You are freezing in the literal structural sense. Fluids freezing, tissues crystallizing. And then the wind. The 2,100 km/h wind does not feel like wind in any sense you would recognize. It is not a push. It is a physical force that moves your body the way water moves a paper boat dropped into a river. You have no agency in it. You are not a person experiencing wind. You are an object in the path of a force, and the distinction matters. At that speed, the air, even the thin, cold mixture of hydrogen, helium, and methane that makes up Neptune's upper atmosphere, carries extraordinary kinetic energy. It tears at anything it contacts, and what it contacts here is you. The surface gravity at Neptune's cloud tops is about 1.14 times Earth's, a little heavier than Earth, not dramatically so. Your weight, in the few moments this question applies, is slightly more than it is now, but it is irrelevant almost immediately, because the wind has already made the question of your weight academic. You are not standing or falling in any controlled sense. You are being moved by the wind and simultaneously falling into deepening cold and pressure. And then it does what every gas giant and ice giant does. It sinks you further. The pressure rises. The cold remains extraordinary at depth, though Neptune's internal heat does push temperatures upward as you fall into the denser layers. And eventually, deep enough, those temperatures would reach ranges that are lethal in the opposite direction. But you are not reaching those depths. The combination of flash freezing and the structural devastation of 2,000 km/h winds ensures that the human body has ceased to function long before pressure and heat become the ruling factors. Of all the dramatic descriptions in this tour, crushed by Venus's pressure, boiled by Mars's near vacuum, falling forever through Jupiter's gas, Neptune's is the most physically accurate to what people imagine when they imagine a violent end in space. The flash-frozen image is real. The supersonic wind is real. The sensation, if sensation lasted long enough to have one, would be something like cold, then nothing, faster than cold. You leave even less trace than you left on Uranus. The wind disperses it. The cold preserves whatever is left in the form of a crystal rather than a body. And then even that is pulled down into the deepening layers by Neptune's gravity, crushed eventually into the mantle's hot, dense pressure, indistinguishable from everything else that has ever fallen into Neptune since it formed 4.5 billion years ago. Neptune, flash frozen in supersonic wind, then sinking into crushing pressure. The farthest planet. One spacecraft once, in 1989, and no human ever. That's 8 planets. And the solar system, remarkably, is not done being interesting. Because before we arrive at the ranking, before we sit with the question of which of these 8 deaths is the worst, and which might be the kindest, and what the honest answer looks like when you lay them all side by side, there are a few bonus bodies that deserve a few quiet minutes, not because they're planets, but because the question of standing on them is too vivid to skip. The moon first. You know the moon, you've looked at it your whole life. It is, depending on where you're listening from tonight, possibly visible right now above you, or behind a layer of cloud, or below the horizon just waiting for morning. It orbits us at an average of about 384,000 kilometers, close enough that we went there with humans 6 times between 1969 and 1972. Close enough that we have footprints up there, 12 sets of them still preserved in the regolith, in the perfect stillness of a world with no wind to disturb them. Stand on the moon without a suit, and the story is very similar to Mercury. It should be. The moon has no atmosphere worth speaking of, just traces, just the faintest whisper of gases clinging to the surface. For all practical purposes, the moon's surface is vacuum. And vacuum does to the human body what we discussed at the very beginning of this tour, the Armstrong limit, the boiling of exposed fluids, ebulism, hypoxia, roughly 15 seconds of useful consciousness. The saliva on your tongue begins to bubble, the moisture in your eyes. You do not explode, but you lose awareness very quickly and you do not regain it. The moon's dayside temperature reaches about 127 degrees Celsius, 260 degrees Fahrenheit, hotter than boiling water, hotter than a conventional oven. Its night side falls to about negative 173 degrees Celsius, negative 280 degrees Fahrenheit. The swing is enormous, though not as enormous as Mercury's 600-degree span. The moon swings about 300 degrees between its extremes. The moon's gravity is 1/6 of Earth's. This is a detail that the human body would actually notice in the brief moments it had to notice anything. You would feel impossibly light. The Apollo astronauts in their suits remarked on it. The strange bounding gait, the sensation of floating between steps. Without a suit, in vacuum, that lightness would be the last thing you felt. The moon, of all the bodies in this bonus section, is the one humans have actually touched, stood on, looked back from, toward Earth. There is something quietly astonishing about that. The fact that we are a species that has done that we have living people who walked on another world and came home and drank coffee afterward. The moon is the one body in this entire tour that is not purely hypothetical for us. We have been there, we survived it, with equipment, with suits, with extraordinary care, but we were there. Next, Pluto. Pluto is no longer a planet. In 2006, the International Astronomical Union formally reclassified it as a dwarf planet, one of several now that we know inhabit the outer solar system. This was controversial. Some people took it personally. But the definition settled around the idea that a planet must not only orbit the Sun and have sufficient gravity to form a roughly spherical shape, but must also have gravitationally cleared its orbital neighborhood of other debris. Pluto, orbiting in the midst of the Kuiper Belt alongside many other objects, had not done this, and so it was reclassified. Its surface temperature is about negative 229 degrees Celsius, negative 380 degrees Fahrenheit, colder than Neptune, colder than any of the 8 planets we visited. It has a thin atmosphere of nitrogen, not enough to breathe, not enough to offer any meaningful pressure, but enough to make it technically something more than pure vacuum. The atmospheric pressure on Pluto's surface is approximately 100,000 times less than on Earth. For any practical purpose, you are in vacuum. You would freeze and suffocate in that order or simultaneously in the same way you would on the Moon or Mercury. Vacuum exposure, ebulism, hypoxia. But at a temperature so extreme that the freezing itself is almost immediate as a secondary process, even as the vacuum does its work first. Pluto is further away than Neptune, sitting at an average of about 5.9 billion kilometers from the Sun, so dim and so small and so cold that NASA's New Horizons spacecraft, which flew past in 2015, revealed a world of surprising geological complexity. Mountains of water ice, nitrogen glaciers, a heart-shaped plain of frozen nitrogen called Tombor Regio. A dwarf planet with genuine character. A world too small and too cold and too airless to host a human body, even for an instant. And then there is the Sun. People always ask. It is the obvious final question in any tour of the solar system. If you can stand on every other body, can you stand on the Sun? No, not in any meaningful sense. The Sun is not a solid body. It has no surface in the way a planet does. What we call the Sun's surface, what you see if you look at it through a telescope with an appropriate filter, the sharp-looking edge of it, is called the photosphere. And the photosphere is not solid. It is a region where the plasma of the Sun becomes opaque enough that light can no longer easily pass through it and escape. It looks like a surface from the outside because light stops coming from below it. But there is nothing there to stand on. It is hot gas, plasma, at a temperature of about 5,500 degrees Celsius, roughly 10,000 degrees Fahrenheit. Vaporized, that is the word. Not burned, not cooked, not crushed, vaporized. The temperature of the photosphere is sufficient to dissociate molecules, to strip electrons from atoms, to reduce matter to its constituent particles. A human body at 5,500 degrees does not die. It ceases to exist as organized matter. It becomes plasma. The atoms that made it up continue to exist, scattered into the solar wind, swept outward by the magnetic and thermal forces of the Sun toward the planets, including Earth. In a very abstract sense, the atoms that make up your body right now were forged in stars, and if you could somehow reach the Sun's photosphere, they would return to something like that original state, dispersed and elementary, carried outward on the solar wind. It is not a comforting way to think about it, but it is accurate, and you would not even need to reach the photosphere for this to happen. The Sun's corona, the outer atmosphere, the vast halo of superhot plasma that you can see during a solar eclipse, reaches temperatures of 1 to 3 million degrees Celsius. The physics of why the corona is so much hotter than the photosphere when it is farther from the energy source is one of the genuinely unresolved puzzles in solar physics. But what it means for the question of standing on the Sun is simple. You would be vaporized long before you reached the 5,500-degree photosphere. You would be vaporized in the corona. You would not get further. The Sun, no surface to stand on, and vaporization waiting before you arrive. The ultimate answer to the what-if question is not even a dramatic confrontation with a surface. It is erasure, clean and complete, before you even arrive at the question. But here is the surprise, the one that saves the tour from ending on nothing but annihilation and cold: Titan, Saturn's largest moon, and the only other body in the entire solar system that we know of where you could, in some meaningful physical sense, almost stand. Titan is extraordinary. Its atmosphere is thicker than Earth's. Surface pressure is about 1.5 times Earth's atmospheric pressure. 1.5 bar, you would not be crushed. You would not be exposed to vacuum. You would not experience ebulism. The Armstrong limit is nowhere near being crossed in the wrong direction. If anything, the pressure is slightly above where humans are comfortable, but not by enough to cause harm. You could walk on Titan's surface without being crushed or boiled. Titan's atmosphere is mostly nitrogen, about 94% nitrogen, with methane and a complex mixture of organic compounds that give its sky an orange haze. It is, chemically, completely unbreathable. There is no oxygen. But as pure physics, pressure physics, Titan is the one place in this entire tour where the question of standing is answered by, yes, the surface is solid, the pressure is manageable, and you would stand on it. Titan also has lakes. Not water lakes. Water on Titan exists as rock-hard ice, too cold to flow. Titan's lakes are made of liquid methane and ethane, pooling on the surface in the same way water pools on Earth, following the same fluid dynamics, filling the same kinds of depressions and shorelines. The Cassini spacecraft orbiting Saturn from 2004 to 2017 mapped these lakes in remarkable detail. Some of them near Titan's North Pole are enormous. Krakenmare, the largest, covers an area greater than the Caspian Sea. Methane rain falls from the orange sky. Methane rivers cut channels into the landscape of water ice bedrock. It is an alien Earth built from entirely different molecules, following the same physical logic in the same way a different language can tell the same story. But Titan's surface temperature is about negative 179 degrees Celsius, negative 290 degrees Fahrenheit, the same temperature as liquid nitrogen. What liquid nitrogen does to a rose, that brittle crystalline shattering, it would do to you, not because of pressure, not because of vacuum, simply because of cold. You would freeze, quickly, thoroughly, fatally, but not crushed, not boiled, not dissolved in acid, not torn apart by supersonic winds, not vaporized, simply frozen. And here is what makes Titan the quiet surprise ending to this tour. If you wore an insulated suit, not a pressure suit, not a full life support system, just something that kept you warm and supplied you with oxygen to breathe, you could walk on Titan. You could stand there. You could look up at the orange-brown sky and see the sun as a dim star and Saturn as an enormous ringed disk hanging in the haze above you, visible but filtered through Titan's thick atmosphere. You could walk to the shore of a methane lake. You could pick up a rock of water ice. You could, in a meaningful physical sense, be there. Titan is the one place beyond Earth in this solar system where standing is not immediately a lethal act by virtue of the physics of pressure or vacuum. The one place where the engineering problem of human survival is merely extreme cold and a missing oxygen supply. Problems that human engineering has already effectively solved in other contexts, rather than the fundamental hostility of a world whose basic physical properties make survival impossible. The one place you could almost stand, negative 179 degrees Celsius, a thick orange sky, methane lakes on the horizon, and Saturn overhead. Almost. Now, the ranking. We have been to 8 planets and 4 bonus bodies. We've stood on the moon, refused to stand on the sun, frozen on Pluto, and found the one almost survivable world hiding in Saturn's orbit. But the original question demands an answer. If you rank the 8 planets by how fast and by what mechanism the human body fails, what does the honest list look like? Let's settle it. Neptune and Uranus, the ice giants, kill you in seconds, flash freezing in the case of Neptune with supersonic winds added, flash chilling and suffocation in the case of Uranus in the coldest atmosphere in the solar system. Both involve sinking with no surface to land on. The distinction between them is marginal. Both are fast, both are cold, both are a falling death rather than a standing one. Neptune is the more violent for the wind. Uranus is the colder. Call them close, with Neptune the more dramatic. Saturn and Jupiter, the gas giants, also kill you by falling, but with different flavors. Jupiter's radiation belts add a dimension that Saturn lacks. You might be fatally irradiated before you even entered the atmosphere. Juno and Galileo, the spacecraft sent to study Jupiter, were built with heavy radiation shielding precisely because the environment around Jupiter is lethally radioactive, even at some distance from the planet. For a human, unshielded, the radiation alone would eventually be lethal before the atmosphere did its work. Jupiter kills you in multiple overlapping ways, which is a distinction worth noting. Saturn's 1,800 km/h equatorial winds, themselves extraordinary by any Earth standard, are fast enough to add their own dimension to the endless crushing fall. Both gas giants are falls into an abyss with no bottom, no hope of landing, just deepening pressure and rising temperature. Neither has a best-case scenario. Mars kills you more subtly, and that subtlety is worth sitting with. You arrive on a world that genuinely looks, in photographs, somewhat like a desert on Earth, red and rocky, wide open, with enough oxygen. In an imaginary suit, you could, in principle, walk around for a while before the suit failed. Mars has a landscape, it has seasons, it has weather, even if that weather is a thin-aired dust storm that cannot actually knock you over. The surface temperature at the equator at midday, about 20 degrees Celsius, is not dramatically different from a cool spring day on Earth. It looks habitable in a way no other planet does. But the air pressure at 0.6% of Earth's 6 millibars puts you well below the Armstrong limit, where your own body fluids start to boil. The ebulism happens immediately. The hypoxia follows in seconds. You'd lose consciousness faster than the cold could even register, faster than the temperature could drop you. Mars would kill you invisibly, with no drama, in an environment that looked almost welcoming. The betrayal of it is the cruelest feature of Mars as a place to die. The false familiarity, the desert light, and then nothing, in under 2 minutes, probably faster. Mercury is vacuum death, the same fundamental mechanism as deep space, the same as the Moon, just with the additional variable of whether you're standing in sun or shadow. In sun, the 430-degree dayside heat is cooking you at the same time. In shadow, the negative 180-degree cold is freezing you. The body fails from vacuum exposure, ebulism, hypoxia, within roughly the same time frame as Mars, perhaps marginally faster, because Mercury's exosphere offers even less pressure than Mars's thin atmosphere. And then Venus. Venus is first. Venus is the worst. Not because it is the most dramatic in the cinematic sense. Neptune's supersonic winds are more visually dramatic. Jupiter's endless fall is more philosophically vertiginous. But Venus is the most total, the most complete, the most immediate, and the most inescapable. At 465 degrees Celsius, hot enough to melt lead, hot enough that the Soviet Venera landers, hardened machines, survived a maximum of 127 minutes on the surface, the heat alone kills you faster than any other cause in this entire tour. 92 times Earth's atmospheric pressure, equivalent to being 900 meters underwater, applies force to every surface of your body simultaneously. The atmosphere is 96.5% carbon dioxide with clouds of sulfuric acid. You are cooked, crushed, suffocated, and chemically burned, all at the same instant. The human body on Venus does not die in any sequential way that allows for a first cause. Everything happens together. The heat, the pressure, the acid, the CO2. There is no last thought, no last sense, no moment of registering what is happening. It is, in the most literal sense, the fastest death on offer. Venus is the most Earth-like planet in terms of size and gravity. You'd feel 90% of your normal weight as you stood there, or tried to. It is the planet most romanticized historically as a potential twin. The morning star, the evening star, the second planet from the Sun, close enough to see as a bright wanderer in the night sky. And it is the planet that would kill a bare human body faster than any other in the most overwhelming and complete way. The reliable killer. 127 minutes was the best a machine, a purposely built Soviet spacecraft hardened against that environment, ever managed. A human body? Seconds? So the ranking from fastest death to slowest, from most total to least, Venus first. Instant, complete, no competition. Then the gas and ice giants, Neptune and Uranus for the cold and the fall, Jupiter and Saturn for the fall and the radiation and the wind, all killing in seconds once you've entered the atmosphere, but with the additional distinction that none of them kill you by standing, they kill you by falling. Then Mercury and Mars at the near vacuum end, ebulism and hypoxia, within seconds to a minute or two, cold following after. The same basic Armstrong limit mechanism with different thermal extremes on either side. Earth, the one world that doesn't kill you at all. And Titan, just off the list, the quiet miracle, the one almost standing world where the physics gives you just enough not to die instantly, but the cold means you'd need help to survive. 8 planets, 8 unrelated ways to die, and only one world in this entire solar system, this whole sweeping, ancient, varied neighborhood of ours, where a bare human body is not simply a problem waiting to be solved by physics, just one, and you're on it right now. That is the thing that comes into focus at the end of this tour, when you've been through the numbers, the temperatures, the pressures, the atmospheric compositions, the wind speeds, the distances, and you sit back with all of it laid out. The solar system is not hostile to life in a careless way. It's not that the other planets simply didn't get around to hosting life, didn't quite manage the conditions. The truth is more stark and more specific. The conditions that allow a bare human body to exist for more than a few seconds exist in exactly one place in the entire solar system. One planet at just the right distance from the Sun, with just the right mix of gases, just the right pressure, just the right temperature range, just the right liquid water on the surface, and in the clouds and in every living cell. The odds of any given world being that world are, based on the sample size of 8 planets, roughly 1 in 8. But that assumes the solar system is representative, and we do not yet know whether it is. What we do know is that in our neighborhood, the count is 1. You are right now at negative 179 degrees Celsius on Neptune's behalf, at 465 degrees on Venus's behalf, falling through Jupiter's endless gas on Jupiter's behalf, breathing the carbon dioxide of Mars on Mars's behalf. Except you are not, because you are here, and here is Earth, and Earth, almost impossibly, works. Your body knows this without being told. It breathes without being asked. It keeps its temperature at 37 degrees Celsius without any deliberate effort from you, managing it through a cascade of biological mechanisms so complex and so automatic that you almost never think about them. Your lungs take in the 21% oxygen that Earth's atmosphere offers and use it, and the rest, mostly nitrogen, just passes through harmlessly. Your cells maintain their fluid balance at pressures they evolved for, at temperatures they expect, in a gravity that built every bone and muscle you have. All of that, the whole quiet working system of you, is tuned to this single world, to Earth. You are not a general-purpose organism. You are an Earth organism shaped over billions of years by the specific conditions of this specific planet, this specific distance from this specific star. Move you to any other planet in this tour, strip away the engineering we've built to compensate, and the system fails immediately in seconds in ways that are vivid and irreversible. And yet here you are, in a bed, or on a couch, or lying somewhere comfortable in the dark, and your body is just doing it. just being alive on the one world that allows it, in the quiet and the dark. There is something in that worth sitting with as you drift. You are not just on Earth in some general sense. You are specifically somewhere on Earth right now, wherever you are listening from, and that somewhere has a night sky above it and a temperature that your body is handling without distress and an air pressure that your ears calibrated to at birth and have felt as normal ever since. Everything about the environment around you at this moment is so precisely within the tolerances your body requires that you don't feel it at all. The most survivable environment in the known solar system feels like nothing because nothing about it is threatening you. That's the quiet miracle of Earth. It doesn't feel like a miracle because it works. We began tonight at Venus in the hook with the lead in the pencil and the pressure of 900 meters of water. We went to Mercury, where the thermometer swings 600 degrees between day and night, and the exosphere barely qualifies as air. We went to Mars, where the desert light is deceptive and the Armstrong limit waits invisibly. We went to Jupiter, falling forever, and Saturn, floating in the imagination's great bathtub, and Uranus, cold beyond measure in its tilted orbit, rolling sideways through the solar system since some enormous ancient collision knocked it over billions of years ago. We went to Neptune, the farthest, the wind-swept, the supersonic, and we found that even the most dramatic death in the solar system is simply a matter of falling into cold and pressure and chaos with no ground beneath you. And then we found the Moon, our companion, with its preserved footprints, and Pluto, the demoted world at negative 229 degrees, and the Sun, where matter itself dissolves into plasma before it can ask any questions. And Titan, the beautiful almost exception where you could walk, wrapped in warmth, breathing borrowed oxygen, along the shore of a methane lake under a butterscotch sky, with Saturn hanging enormous and ringed in the orange haze above. All of it is out there right now. Every planet we visited is occupying its orbit, following its path, being exactly what it is. Neptune is being swept by 2,000 km/h winds in total darkness. Venus is cooking at 465 degrees under its crushing blanket of CO2. Mars is cold and thin and quiet under its pale salmon sky. Titan's methane lakes are still and dark and utterly calm. And you're here. Wherever here is. Somewhere warm enough and pressurized enough and oxygenated enough that the entire system of you is just quietly running. Wherever you are listening from tonight, whatever corner of this improbable blue planet has you horizontal and drowsy right now, I hope the tour has given you something to carry gently into sleep. Not anxiety about the cold of Neptune or the acid of Venus, but the slow settling sense of what it means to be exactly where you are. The weight of an ordinary night, a familiar pressure, air that needs no decoding. If you've made it all the way to Neptune and beyond, thank you for staying. And if you drifted off somewhere around Saturn, that's perfectly fine too. The planets will be exactly where you left them in the morning. If this slow tour through the solar system was the kind of thing that helps you settle in for the night, a like and a subscribe means more than you might think. Small creators like me rely on your support to keep these quiet journeys going, and I'd love to know too, where in the world are you listening from tonight, and which planet surprised you most? Drop it in the comments when you wake up, if you remember. Until then, good night from up here in orbit. I'll keep watch while you drift.